quick overview. After a short introduction, we'll give a quick overview of the actual zones that are relevant for fire in helicopters and the corresponding certification requirements. And then we will focus on one of those areas for one particular application of composites in a slightly unusual way. When I say we, that's because I will be presenting together with my colleague Manuel Kempf. Manu?
Yeah, hello, my name is Manuel Kempf. I'm working Airbus Helicopters Materials and Process Department as a composite materials expert, with also some focus on high temperature materials and fireproofing.
Yeah, and my name is Martin Latzak. I'm also working in an expert role, but in the airframe design department, also focusing on composites, and I have been involved in several developments in the recent time. So we work for Airbus Helicopters, the world's #1 helicopter manufacturer. And we design, build, and support a lot of nice helicopters. The latest one being the H160. That's a twin helicopter in the 6-ton class. And this has just recently been certified, and it features a mostly composite airframe. Here you can see it again, and I'll use this as an example to give you the different zones that have fire requirements. So this is driven by the certification specifications CS29 and CS27, or the corresponding FARs for the FAA scope. And the first zone is actually not a geometrical zone, but any area where flammable fluid can leak and create a fire hazard. So this is governed by paragraph 863. And this has two requirements. The first one is to minimize the probability of a fire occurring. And the other one is not regarding any probabilities, to minimize the effects of a fire when it does occur. And usually you do that by, for example, limiting the ignition sources, providing proper drainage to limit the amount of flammable fluids that can accumulate. But then you also have to show that any structures are able to sustain and contain the fire. And the good news regarding composites is that if you have composite parts sized for the flight loads, or in the case of a cowling, for example, for burst strike, this, for us, usually covers that requirement as well. And one of the main areas, obviously, that is affected by that requirement, sorry, is the upper deck with the main gearbox. The next zone is the interior, which is described by paragraph 853. And for that, the requirement is pretty straightforward. Materials have to be self-extinguishing. And it's also pretty straightforward for composites if you use a resin that contains flame inhibitors. The next zone is the cargo and baggage compartment with paragraph 855. And for that, the requirement, in addition to the compartment requirement, if it's connected to that, is to be fire resistant, which means it has to sustain a fire for 5 minutes. And an even more restrictive requirement is given by paragraphs 1191 and 1193 for the designated fire zones. In the H160, that's the engine, where the fire has to be contained for 15 minutes. So the designated fire zone is defined as any zone containing an engine or an auxiliary power unit. H160 doesn't have that. And the paragraphs give the requirements for the firewalls and cowlings. They have to be able to sustain a fire for 15 minutes to be considered as fireproof. The firewalls also have to contain the fire in that they do not allow any hazardous quantity of air, fluid, or flame to pass them. And in addition to those very obvious requirements, there are also, let's say, more unspecific requirements that can be summarized as there must not be any severe consequences of the fire, even in adjacent zones or with adjacent systems. So, for example, even under fire conditions, the flight loads have to be sustained. Even under fire conditions, essential systems must continue to function, and so on. So usually, to answer that, if you use composite materials, again, if you have a flame retardant additive in the matrix and you size them with a sufficient thickness, this can be shown. Another way is to go to metallic parts. So some materials like steel or titanium are basically fireproof by definition in terms of burn through. And of course, the additional effects of the fire on the adjacent systems have to be substantiated as well, either by test or by analysis. And when we're talking about fire testing, then this is done according to the ISO 2685 that we'll come back to later, or equivalent FAA procedures. And this has to be done on part and assembly level. And this assembly level thing makes it a lot more complex. So for the actual implementation of that, I'll hand over to Manuel.
Okay, so now we've heard about requirements in the designated fire zone and how to answer them. But which parts are we talking about in detail? So when we have, so let's have a closer look to the helicopter. Looking from the outside, of course, the first parts from the engine compartment we see are the cowlings, which are usually carbon composite structures. They represent the loft of the helicopter and also separate the engine compartments from the outside of the helicopter. So they are part of the engine compartment, and as Martin already said, therefore need to be fireproof. Inside of the helicopter, we have the firewalls, which are these parts here shown in green. There are several ones, for example, the center firewall, separating both engine compartments from each other, but also the forward and the aft firewalls, separating these engine compartments from the rest of the helicopter. So to the forward direction from the main gearbox deck and to the aft from the exhaust compartment. But there's also a further firewall, which is called the engine deck. This is not only a firewall, this is also a structural part of the helicopter airframe, which makes it a little bit more complicated because this part has also to sustain some significant loads in a case of a fire. So usually for the regular in-service operating condition, it's therefore a bit oversized because, as said, it has to sustain also the flight loads in case of fire, meaning at temperatures above 1000 degrees C. And there may be even some parts which are outside of this designated fire zone, but which could also be affected in case of a fire. And this is the case here in the nature of the engine frame. Martin, maybe you may show its location. The engine frame where the engines are attached to is not made of a fireproof material. This means it needs to be somehow protected from the heat generated during a fire event because it's directly located underneath the engine deck. So there is no fire passing through basically, but there could be, or there would be, considerable heat transfer, meaning there's a risk, or not a risk, it could lead to an overheating of this part, which must be avoided. So the fireproof testing itself on the next slide is maybe already known to some of you. So it follows certain specific standards like the already mentioned ISO, also some guideline material as the advisory circular. And in these standards and guidelines, all the requirements and boundary conditions and test parameters are defined according to which we have to perform the fireproof testing. So first of all, most important parameter is the kerosene burner, which is used to generate a flame of 1100 degrees C. And what is also quite important, a heat flux of 116 kilowatts per square meter. Second important requirement is the vibration, especially for our helicopters. We have to apply vibration throughout also test. And this could be crucial for some assemblies, but also, for example, for composite materials regarding burn-through behavior. Fireproof rating is given when the material or the test article or the assembly or part passes the 15 minutes of the testing. Passing means there must be no burn-through. there must no flame occur on the backside of the test article. And during the test, that must not be a significant increase of the flame pattern. Yeah? And additionally, after stopping the test, meaning removal of the burner, the test article may not or is not allowed to kind of burn further or reignite after the test. So this slide now gives an example of a basically successful test, which also had some non-successful features, let's say. So the test was intended to exactly test this engine frame protection, which I mentioned earlier. You see this on the left-hand slide on top or between the burner and the engine deck. Yeah? And on the right-hand side, we can see quite well that in this area where on the fire side the thermal protection is located, it looks quite good. And also the temperatures were in the range we would need for this part. But additionally, there were still observed some flames on the backside. So this means from an overall perspective, this would have been a fail. But these flames occurred in an area which were not yet protected in this test, because the test was mainly intended to test this thermal protection of the engine frame. Nevertheless, we need to address this issue, and these flames were identified to come from some outgassing of a sealant, which is used to seal the rivets to get the engine compartment fluid tight. And this outgassing subsequently ignited on the hot metal surface of the backside. So somehow these flames need to be contained. There could be different strategies. Just to add another barrier, another firewall, which would be basically possible, but also challenging both in terms of architecture and also weight. Avoiding the outgassing source at all is not possible, because we need this organic material, this sealant, because the engine compartment needs to be sealed to be fluid tight, that in case of a kerosene spill, for example, no kerosene could leave the engine compartment in an uncontrolled way. Avoiding the ignition source would be another option, but this means to cover the whole engine deck, for example, with a quite heavy protection as used to thermally protect the engine frame. And so as a final strategy, we kind of decided to just prevent this backside from developing ignition conditions, meaning we must not have a concurrence of this ignitable gas mixture and an ignition source. So somehow managing the heat transfer to decouple these two events on a timeline. So to have, for example, outgassing first, and after that we may have rising of the temperature to ignition point, but then the outgassing has already finished, so we wouldn't encounter this flame issues. So it was quite clear that we would need some kind of light insulation in this area. And there are basically different options to do so. From a material perspective, first we would go for a lightweight, meaning low density material with quite low thermal conductivity. There are material existing. We did some screening or investigations on such material in the past, like this alkaline earth silicate materials, also called superwool, which is like fibrous mats. Also basalt fiber, cork materials, carbon foams. But all these materials have somehow could not be used like freestanding. They need to be somehow covered or sandwiched between some skins as well, composite skins in this case. For example, you see also here like density and thermal conductivity of a standard CFRP laminate, which is kind of different in orders of magnitude, but we'll come later to this. So, but the effective thermal insulation performance, of course, will depend on the thickness of the insulation material, the material itself, its properties, and also the testing conditions or changing properties during test. So when we're talking about cork, for example, it will degrade during the testing and therefore also change its properties and therefore the heat transfer and so on. So in our case, we decided to go for this green boxed material since we have low thermal conductivity, low density, and also high temperature resistance temperature resistance in the range of the temperature of the fire. Full-scale tests were quite successful with these blankets, with these sandwiched blankets, both on metallic as well as composite structures. We could avoid the backside ignition. We could quite significantly reduce the temperatures on the backside. So overall, quite promising concept with a good performance. But nevertheless, due to the fibrous nature and the sandwiching, we had some integration challenges and also robustness concerns. For example, during maintenance, when a mechanic would step on the engine deck on this protection, there was considered to be a certain risk that this protection could be damaged. So we're still working on this topic to overcome these issues. But for now, we also found another quite interesting solution, which is a little bit less effective on the one hand, but on the other hand, a quite reasonable compromise between performance and in-service and maintenance requirements. So now I hand over to Martin again, who will continue.
Yeah, thanks, Manuel. So we were thinking about different alternatives due to the constraints mentioned. And one very obvious solution that we came across is intumescent paint. So that's a paint that blooms and increases in volume under fire conditions and so forms an insulating layer. However, in our application, this had several drawbacks. One is that we were talking about a titanium deck where the adhesion is not really good. And the other thing is that, again, due to robustness, people stepping onto the deck, some damages occurring during maintenance, we would need some kind of touch-up procedure, and the process time to touch up on this kind of paint is more than a week, which is clearly not acceptable for a customer. So we started thinking about our other applications of this paint, for example, on composite cowlings. And we thought, okay, why not use composite material just as a substrate for that paint? And at the same time, also create a separate part that you can just exchange when it's damaged. So we went for the really minimum layup that we were able to design. So that's 2 fabric plies of carbon composite, painted with this intumescent paint, just to install it on the deck. And the result is something that you can see in the right-hand corner. It was almost successful. It was a lot better than the original test. Nevertheless, we had some very small ignitions. So you can see the red circle so that you're pointed to it. It's almost invisible, but nevertheless, formally it was a failure. So we needed to reinforce. And when we thought about how to reinforce, we also saw that during the initial test, the intumescent paint is gone after a while because we're testing with vibration and it's just shaken off by the vibrations. But the carbon still sustained some kind of protective layer there. So we thought, okay, why not do one test with a solution that completely removes the intumescent paint and just uses the carbon composite? So we designed a reinforced plate with a higher thickness. And in the end, this was actually successful. You can see the pictures at the bottom. So it's really just a carbon laminate with some additional fibers. In the center, you see the state at the end of the test, so after sustaining 15 minutes of this fuel burner. And there were no ignitions. So this was a real success in the test required for the certification. And the nice thing about that is, in addition to being removable, to being something easily interchangeable, that due to the composite part, you have a lot of freedom and you can do a lot of things. So in here you can see the raw part of one of those protections from the bottom side that is face to face with the engine deck. And you can already see that we integrated a lot of individual small features, so joggles going around that we need for maintenance purposes. We also have a requirement to take care of proper drainage, so not to collect large amounts of fluid on the deck, which is why we have those interconnections that allow drainage of the deck. And here you can see the actual installation situation of that part in the helicopter. And because it is actually a structural material, for example, we're able to install systems directly on this protective layer, like in this case, the fire detection line. And as Manuel mentioned, a big focus on the H160 is on maintainability and support and services. And because it is structural, you can actually walk on this part, and it's pretty robust. It will not be damaged by just stepping onto the deck, which makes it a lot easier for maintenance personnel to work on the engine. So in this case, actually, even though we have a metallic structure, we were able to reinforce and protect it with a composite part that really gives the best solution for this particular installation situation. So that's it for us. Thanks a lot for your attention. And we used the 20 minutes, I think.
Yes, thank you very much for your interesting presentation. We already gathered 2 questions. I also had noted some down, but as you mentioned, you already covered the 20-minute slot. So I would suggest to follow the initial idea to ask the questions at the end, and so after the next 2 presentations, and continue with our next speaker, who is Professor Christian Brauner, or as we call him since today, Professor Christian, from the Fachhochschule Nordwestschweiz. So it's a University of Applied Science and Arts, Northwest Switzerland in English, who was part of the SuCoHS project, and who will say something about the material developments that were conducted within the project. So please, Christian.
Thank you, Professor Benedict. So hello, everybody. I would like to tell a little bit about our material development, especially for high temperatures resistant composites. So we have seen in the previous talk a nice application, and there were not the question what type of resin they used, but maybe this resin which we show today could be a nice material for them as well. So what we have done here was that we did or modified a cyanide ester resin, and which was then tested and used in the project itself. So just as a short introduction, my colleagues and me, mainly Markus Kroh, Lersan Amirova, Fabian Schad, Nicholas Gord, who worked on the project. We are working at the Fachhochschule Nordwestschweiz. Okay. And we are somehow... Sorry? We are somehow 45 people covering all the value change along composites, starting from material development up to building demonstrator. The demonstrator where we focused on in this project were related to the NASA component. So here is the old name Bombardier mentioned. There was a transition from Bombardier to Spirit, so this was related to Spirit. And then one end user case from Aeronover, which is a tail cone panel substructure in the APU unit. And as you can see here, the requirements are very high. So the glass transition temperature somehow should be above 300 degrees in both application. It should be processable, and there I mentioned the curing temperature in a standard autoclave system. So that you can use the material with the equipment which is available at the end users, so that you don't have to buy a new autoclave which goes up to curing temperature above 200 degrees. Then the fracture toughness should be high to have a damage tolerant structure. This is really a challenge, because if you have systems with a high glass transition temperature, they are most of the time super brittle. And I will come to this in a moment back. And then the material should itself be processed by advanced fiber placement or automated fiber placement. And additionally, for the use case of Aeronova, it should be fireproofed with the same test which the colleagues from Airbus helicopters have shown some minutes ago. And so we first started with a review of existing materials on the market. We derived some needs from the end users. We prioritized them, and we compared the needs to existing systems on the market. And so here you can see a lot of different materials. And please remember that the dry glass transition temperature for Bombardier, for Spirit, and for Aeronova should be above 300. And if you now cluster the materials a little bit, then you have mainly 3 classes which come in the region where you could sustain, or where you have a glass transition above 300, which is BMI, cyanide ester, or polyamide. And if you have a closer look, only polyamide and cyanide ester come above 300 degrees. And so we selected somehow cyanide ester as a promising material system. Also because we had some previous experience with cyanide ester. And as you can see here, when you look at the different cyanide ester systems, you see clear a difference between them. And the difference there is based on their raw material which are used for the production of cyanide ester. So some of them are based on bisphenol A. They are a little bit lower in the TG itself, or there are some Novolac systems, and these systems have a really high dry TG going up to 400 degrees. And so we started with base system. So these cyanide ester, which you can see here, which is Novolac based. It is somehow a system which has a glass transition temperature above 400 degrees. But the drawback is that it's very, very brittle, and that you have to cure it at really high temperatures in the end. And so the first investigation which we have done was to change a little bit the curing behavior, and we used a kind of catalyst to enable that you can cure the system initially in an autoclave at 180 degrees to have a sufficient degree of cure and glass transition temperature. But later on, you have to do a post-curing, but it's possible to do these post-curing freestanding in an oven, which is then okay. And there you have to apply around 260 degrees, 250, 260. So we investigated different catalysts and different modification, and finally we derived one formulation, and also we derived the curing behavior, which was later then used by colleagues to do process simulation, to investigate the curing behavior in the autoclave and to compare it to the monitoring system from Synthesize. Then we started a huge work package to evaluate different toughening systems. And here you just see the results. So I don't show everything which we have tried. We have tried a lot, believe me. And also my colleagues were sometimes really frustrated. But we found one promising candidate, thermoplastic additive based on a powder, a polyethersulfone. And with this thermoplastic additive, it was possible to increase the fracture toughness, as you can see here. And starting from the base formulation, we were able to double nearly the K1C value. And if you take a look closer to the fracture surface, you will see a nice formation or separation of the thermoplastic elements. So here, these regions are the polyethersulfone, nicely distributed, and they work really as a crack stopping element in the resin itself. So the crack really goes into the thermoplastic region and is then stopped because the thermoplastic material is not as brittle as the cyanide ester itself. There's a nice publication if you would like to gain more knowledge about this. Then we investigated somehow the temperature behavior, and the drawback most of the time is if you add a thermoplastic material with a lower TG, then your final TG drops. And here you can see the temperature or the storage modulus, the elastic behavior of the base resin with the high TG of 400 degree. And if you add a higher amount of thermoplastic materials, then it might be that you have higher regions of these thermoplastic zones, or maybe there could be a change of the morphology that you end up not with these islands here, maybe with higher region, and this will drop your final TG. Or you will have two glass transition temperature. And so we had to find a certain compromise, and we ended up that 15% of polyethersulfone is something which is acceptable with a small drop here around 250 degree, which is the TG of the polyethersulfone. Then we continued, and later on, Thomas Ricard from NTPT will give a talk about thin ply. So NTPT is a prepreg manufacturer who's able to spread tows that you can use the thin ply effect. He will give more explanation about this later on. But we were able to create a prepreg with an area weight of 67 GSM and fiber volume content of 55% using T800 fibers with our resin. And then we tested this as well on a Coriolis AFP machine at the NLR, and we are able now to place with these AFP machines our resin system, and this was later used in the demonstrator as well. So it was a kind of modification, iteration to modify the viscosity. If you add thermoplastic materials, viscosity always goes up, and you have to align this with the needs of the Coriolis tape AFP device to have a certain degree of tech, so that you have a robust process. So I think Wilco Gerlitz from NLR will give a lot of details there about the tape, the fiber placement. Then we started to test our material after curing, and here you can see some of the results which might be very interesting for people from Airbus helicopters. So of course we have our initial properties at room temperature, in tensile compression, in fiber direction, transfers to the fiber direction, and shear. And then Martin Liebisch, the colleagues from Deal Air, started to test the material as well at higher temperature, up to 250 degree or above. And here you can see now a little bit relative modulus over the temperature to that we can compare it a little bit better. And what you can see is that in fiber direction, there's not much influence of the temperature, but transfers to the fiber, especially in tensile, you can see a drop in the region where you have the glass transition of the polyester foam. But when you compare the compression behavior, you don't see such a large influence, and the shear behavior is somehow or also more linear dependent. But still, at 250 degree, you end up with quite high values. And if we take now a little bit the look to the strength properties, you can see as well quite high properties at room temperature, similar to a standard material. And then if we take a look to the temperature behavior, we see that in fiber direction in tensile, we don't have a huge drop of the strength, but all properties which are related to the metric itself, so transfers, they of course drop to a certain amount after 200 degree. So and you can see here that also everything which is metrics dominated is somehow critical above 200 degree. This highlights a little bit also when we take a closer look to the interlaminar shear properties. So here you can see, in detail a little bit the transition. So you at room temperature you really have brittle failure, but at higher temperature it changes totally to a more ductile behavior, as you can see here with these move failure curves. And it's really initiated above 200 degree. Then last, we investigated also the degradation behavior in long term. And for this, we placed our formulation in comparison to a BMI system, which was a kind of baseline system, into an oven for 4 weeks, and we performed weight test and as well interlaminar shear test. And what you can see here now is the comparison of the two systems at 250 degree and 300 degree, and we see a certain weight drop of the cyanide ester as well of the BMI, and if we benchmark the two systems, we can clearly see that the cyanide ester has a better behavior, and as well we observed that the BMI was showing a lot of cracks at the cutting edges of the samples, which were not visible for the cyanide ester itself. And then last, we performed these ILS tests after this aging, and there it was visible that we do not have a huge degradation, or we have a degradation, but this degradation is somehow linear over temperature, as you can see. And if you compare this somehow to the BMI system, the BMI starts a little bit at the higher level here, but drops much faster over temperature than our cyanide ester system. So would like to conclude. So what we have done was we started with a resin system, which is commercially available. And this was then modified in the curing behavior to fit to standard aerospace equipment. Then the system was toughened, and we reviewed different tougheners, and it has now an increased toughness. Out of this, we modified the viscosity to produce a thin ply prepress system, which is possible to be used of an automated fiber placement device. And we have some knowledge about the high temperature behavior and also about the long-term thermal behavior. And later you will see more insight of this, or yesterday you already have seen that this panel, which was manufactured by us, was passing this flame fire test. To use a flame 50 minutes on the panel without any burn through. So, but I think Inigo today will tell a little bit more in the afternoon about it. So I hope I'm in time a little bit. And
almost
if you
perfectly in time, yeah.
Yeah, if you have any question, yeah.
Yes, there's already a question in the chat, but since we're just a bit behind time, I would suggest to keep the original plan and ask the questions in the discussion round afterwards. Right, so thank you very much, Christian, for the talk. And I would now like to hand over to Hans Heudongs, who's working for TFC, for Transference Chemicals, and who was also involved in the material development within the SuCoHS project. Hans, the floor is yours.
Hans, we cannot hear you.
Now you hear me.
Yes.
Okay, sorry. I turned on my video and I forgot to turn on my mic. My screen is showing. That's also good.
Yes, very well.
Okay, then I'm good to go. So again, good morning. Thank you for the place to tell about our results that we obtained in the SuCoHS project. My name is Hans Heudongs. I work for Transference Chemicals. We have been part in the SuCoHS project as a material developer, developing the polyfurfural chemistry for high temperature composites in fire safe applications. Okay. I will first tell something about the company that I work for, just to give a general introduction. A little bit about the polyfurfural itself, what it is and what it is good for, where it comes from, and then I will elaborate on the specific development that we did within the project. So we selected one of the use cases in the project to test our composite chemistry for in 3 different steps. The company that I work for, Transference Chemicals, we are the world leading producer of furan-based chemicals, and we're located in Geel in Belgium. We've been here in this location already for 45 years, almost 50 next year, in the production of both furfural and furfural with a capacity of 40,000 tons every year. And we are an innovator since a few years in the development of polyfurfural as a thermoset resin system for adhesive and composite applications. It's a relatively new application for us as well. Where are we? So we're in Geel in Belgium. So just to situate it, it's between Antwerp and Liège, next to the Albert Canal, where we operate a chemical factory. But our raw materials for the chemical factory originate from biomass. So we are, our chemistry is strictly biosourced. There are no petrochemical routes to make the chemicals that we manufacture here in Belgium. The initial raw material for our chemistry is predominantly, not solely, but predominantly is sugarcane. Sugarcane is planted in the world to make sugar. That's the primary objective why you plant sugarcane and you harvest it. When the sugar is extracted from the stems, from the plants itself, there is a waste material, and that waste material is called bagasse. It's a fiber structure, and the bagasse contains C5 sugars, or hemicellulosic sugars, and via a thermal process or thermochemical process, those C5 sugars can be converted into furfural. So it's like a dehydration reaction which takes place on the C5 sugars. C5 sugars itself, or hemicellulosic sugars, are unedible for humans and most animals, so they have no real value unless the calorific value, or in our case, to make a chemical from. So the first step is converting the hemicellulosics in bagasse to furfural. It's done in a thermal process, as I said, distilled to high purity. So our raw material that we start our chemistry from, furfural, is a high purity chemical. So it's not a collection of different biomolecules. It's a pure 99.5% pure chemical. That is a liquid, comes to Belgium, which we hydrogenate to furfuryl alcohol, and furfuryl alcohol by itself is the starting material for our chemical platform that we operate. Now, the question would be, is only sugarcane usable to make these chemicals? No, it's not. Our own source that we operate is based on sugarcane, but for example, there is still a lot of furfural production in Europe as well, where furfural is made from waste wood, for example. So it's not solely based on sugarcane. Now, the next step from the agriculture and the chemicals to the polymers, it's a simple step that we take. As I said, we make first furfural, then furfuryl alcohol. The next step is to polymerize furfuryl alcohol. So furfuryl alcohol is a self-reactive molecule, and it can be polymerized. We do that in a controlled fashion. So we can make out of furfuryl alcohol polymeric structures, and these polymeric structures are liquid or highly viscous, but liquid thermoset resin systems, and they can be cross-linked with themselves in order to make a macromolecular structure. This mechanism, so the product itself is polyfurfuryl alcohol. This is the polymer that will be impregnated in the next slides in carbon fiber to make prepreg, but this is the workhorse polymer in order to make materials out of. Now, the polymer itself needs to cure and needs to harden, because as we supply it, it's still a liquid. It needs to thermoset, and the thermoset reaction itself is a complex condensation reaction which takes place amongst the polymers in the red formulation. We have initial polymer chain growth, whereby polymers link to one another with the split of a water molecule. So it's a true polycondensation reaction system. Initially, the chain growth is somewhat linear, but there is also branching taking place. So a substitution of the linear chains with chain growth at its extremities, both on the aromatic and the methylene bridges between the furanderings takes place. And then most importantly, there is a Diels-Alder cross-linking happening at higher temperatures between the polymers, which you see here. You see here Diels-Alder bonds being formed. The Diels-Alder bonds are an intrinsic part of the polymer building or the macromolecular polymer building mechanism, due to the fact that this Diels-Alder product itself can be dehydrated again at a high temperature, which forms C6 aromatics, which you see here on number 5. And these C6 aromatic structures are thermally irreversible, which gives you polymeric structures with a very high TG value. The way how we control the TG value of our of the polymer in a composite application is to control the degree of Diels-Alder dehydration and to build more of these C6 and cross-linked polyfluoroalkyl alcohol structures. I will come back to that later. The formation of this C6 structure, again here, is also the way to make carbon out of these polymers. So the polymers, PFA cured polymers, also have a tendency to make carbon at high temperatures. They have a carbon yield of around about 45% upon pyrolysis conditions. So technically, PFA resins and also in practice are being used to make carbon as well. So let me go to the next slide. Something about how it is employed and how it is utilized, about the properties. So PFA polymers are produced as a pure polymeric material, unformulated. They are liquid, as I said, and they need a hardener to be activated and to cure. Now, the most used hardeners for these polymers in prepreg applications are amino salts, and the way how we control the curing kinetics of these polymers is by just increasing or decreasing the acid strength of the amino salt. That's the only thing basically to know about how to activate these PFA resin systems, is either increasing the acid strength of the amino salt or decreasing the acid strength of the amino salt gives you a certain curing temperature. Curing temperature of these polymers can be basically anything starting from almost 100 degrees C up to 200 degrees C. As I said before, TG values of these polymers are controlled by the cross-linking the degree of cross-linking that you put in the cured macromolecular structure. And the degree of cross-linking can be controlled by either the selection of catalyst and also by the post-curing temperature. What you see here, and I have a more elaborate slide on this as well. Material which has been cured at a low temperature for a very short period of time. This is the red curve is a storage modulus curve of a part being cured at 1 hour at 80 degrees C. Has very little mechanical stability at higher temperatures, but as soon as post-cure temperatures go up for a longer time, this is a specific formulation post-cured at 110 degrees for 10 hours. Then in this specific case, the TG value is almost invisible up to a temperature of 180 degrees C. So it's very susceptible to exposure to temperature and the kind of catalyst that we use in order to activate the PFA resin system. That has been an integral part of what we have done in the SuCoHS project as well. So playing with these features allowed us to propose solutions to all the problems that we encountered in developing the materials for the SuCoHS project. The scope of our work in SuCoHS was the development of a PFA carbon fiber composite in AFP manufacturing, so an automated fiber placement manufacturing. The demo in this specific case was an interior shell, an aircraft interior shell, which had to, on one hand, which had to comply with fire specifications. So a lot of our time went into making the carbon fiber PFA structure passing the relevant fire testing. This, in our case, was FAR 25853 testing, OSU testing. And on the second part, or in the follow-up of that development, it was making the material work in automated fiber placement. So the overall objective was, of course, to make the material resistant to fire, but also to have pre-preg tape made with carbon fiber, unidirectional pre-preg tape, in order to be handled by a Coriolis AFP machine, and to make it into a structure which was fiber placed, which took for us half the time of the project in order to make that compatible. At the end of the project, we also performed a lot of high temperature resistance testing, which I will come back to as well. The fire resistance testing was specifically targeted to have carbon fiber reinforced material passing fire specifications. There we used a bottoms-up approach. Our initial testing showed that unformulated or a workhorse formulation of PFA resin system in combination with carbon fiber was close to passing, but did not quite yet pass the fire specifications. So we had to redo the resin formulation. In that respect, we used a bottoms-up approach, starting with TGA DSC trials. Then we did a lot of direct fire testing in the lab scale, because our lab technicians love to burn things in the lab, so they did a lot of Bunsen burner tests. And we went to concalorimetry at higher heat flux, initially at 50 kilowatts per square meter, to test the heat response of smaller panels. And then we went to larger scale panels in order to test it according to FAR testing methods, which in the end we passed. So that's the good news. That's a bit of a spoiler. What we did initially is combine TGA DSC testing and evaluating the heat release coming out of a burning resin sample. We saw that by changing the formulation of the PFA resin systems, we could very well control the heat release from the samples, but also the peak heat release from samples. So the just ground and pulverized PFA, cured PFA polymer, which was subjected to a combined TGA and DSC analysis. And that led to us selecting a certain recatalyzed PFA formulation. And just by changing the catalyst in the PFA resin system, fire performance could be influenced a lot, especially with carbon fiber. The reaction or the change of fire performance with a change of resin formulation was quite specific and important. This is a small movie which I'm showing. The PFA1 is a not optimized formulation of PFA. The PFA2 is the one that we selected for further development. This is a direct contact with a Bunsen burner, and you see after the flame has stopped, the PFA2 formulation with an optimized catalyst extinguishes immediately. So there is even no more after flame present with that resin formulation on carbon fiber. Next step for us was to upscale this to larger scale pre-preg manufacturing and make large panels. Initially tested in concalorimetry at 50 kilowatts per square meter. There we also saw that the PFA2 formulation with an optimized catalyst formulation had also in concalorimetry a lower total heat release and a lower peak heat release value in ISO 5660 testing, quite low actually. And also there, the when we tested PFA2, so the second PFA formulation in larger scale prepreg at 45% resin content, testing according to FAR 25853. Very good results were obtained. So with a total heat release of 5 kilowatts minute per square meter and a peak heat release of 40 kilowatts per square meter. So both of them passing easily the 65 mark that they needed to pass, but also, and maybe also important, is the low smoke density. So it is not a by changing the resin formulation, the catalyst formulation, a PFA resin system. It's not that you're making a purely choked situation of a burning resin system, which provokes a lot of smoke. The smoke density even went down by improving the reaction to fire. So that was an initial good result that we obtained within the project. Which for us was a result which stood by itself. We were quite happy with that. But then we went to utilizing this specific formulation in automated fiber placement, and that was a story by itself. So we before we made prepregs in woven fabrics, which by a hot melt prepreg manufacturing. Then we had to change that manufacturing procedure in order to make unidirectional tape, and not only unidirectional tape, but unidirectional tape which ran on the Coriolis machine of NLR in the Netherlands. And in the first formulation that we made from this, or the first attempt that we made from this formulation was tape prepreg, but it was not up to its task in a Coriolis machine. Initially, we had a lot of fiber separation from the tape. We had a lot of resin transfer on the mandrels of the Coriolis machine, and that basically was solved. By maturing, increasing the molecular weight of the resin system in the tape prepreg. That's what took us a few months in order to get it right, is to define the molecular weight the resin system needed to have in order to make it processable on an AFP machine. So after a few trials, that was quite successful. The first demo, or the first test that we made, was a 6-stringer stiffened panel. That was one of the test super component test materials that need to be made for Rockwell Collins for the interior shell. And that was made by AFP. So you have 2 layers of woven PFA carbon fabric, and the stringers are printed by the AFP machine. And that, in the end, that went quite well. That's I think Wilco from NLR will have more movies about fiber placement, so I'm not going to go too long with this. But this is the manufacturing of the 6-stringer stiffened panel at NLR with PFA tape. I think it goes one more time. That went well in the end, and the initial issues that we encountered in the beginning of the project by unraveling and by resin deposit on the machine itself, those were solved. So that was in the end, we had a quite well-functioning AFP tape material from polyfish alcohol in carbon fiber. The stiffened panel was also tested to in specific strength and specific stiffness. So that's weight correlated, or weight correlated strength and stiffness, which had good results, to be honest. If comparing it with a standard sandwich structure, in 4-point bending, the 6-stringer stiffened panel had a high strength and a high stiffness. That was a positive result for us passing this this milestone in the project to make an AFP processed panel, which after curing in a vacuum bag had the right strength and stiffness to it. After we made just a flat panel with 6 bars of stiffness printed on top of it, we also went into more a demonstration object. This was the risk mitigation structure that was also shown by Rockwell Collins yesterday. Again, there the overall material composition is the same as what I showed slide before, but now printed in a more complex shape. Also there were no issues with placing the PFA unidirectional tapes, even with curvatures that you see over here. So it could even follow quite easily. It could go around the corner if you see it like that.
Hans, we're a bit behind time already.
Okay, yeah, but I'm coming to the end, Ben. Don't worry. 1 minute, okay. The final part after AFP manufacturing was also vacuum bag cured and yielded a nice demonstration object with no delamination. So that was a quite successful, or a very successful ending of our development of AFP processing. Just a short note on the high temperature testing that we did as a follow-up of our activities in the project. As I said, by controlling the post-cure temperature of PFA, the glass transition temperature can be pushed to very, very high temperatures, well above 300 degrees C. What you see here is these are DMA results of PFA cured at, for example, at 180 and 220 with a quite flattish TG curve, so not a lot of transitions taking place when the material is cured at a high temperature. And together with DLR, and that's basically the last slide, we did we repeated those trials, but then not trying to evaluate glass transition, but looking to interlaminar shear properties of the laminate. And there, although the absolute interlaminar shear properties of PFA resin systems are not very high, so you have something between 25 and 35 megapascals. But if you plot that relative in function of temperature, then, for example, this green curve that you see here, so the army green that you have here, the green curve here shows that interlaminar shear properties of PFA being post-cured at 180 can survive can survive temperatures well above 200 degrees C without a dramatic drop of interlaminar shear strength. This is certainly something, so this was found at the end of the project. This is certainly something that we will take forward in new research, so to further optimize and to further understand these properties of PFA matrices at high temperatures. That is, I'm coming to the end of my presentation. I think the conclusion speaks for itself. So we optimize the fire resistance of PFA resin systems in combination with carbon fiber. We together with the partners, we made it AFP processable, which took some trial and error work, and in the end we made the demonstration structure that was a part of the overall project objectives. That's it, Benedict. So that leaves me to thank everybody that we work with within the project, and I hope I did not go too much over time.
Thank you very much, Hans. Yeah, well, it's always an accumulation of delay, right, at the end of a session. So let's straight jump into the question round, and I would like to start with questions to Airbus Helicopters colleagues. We have also some questions to Christian, who already answered them. So yeah, the first question, and maybe that is to Martin Lazak, is how does the choice of the insulation material affect the overall design concept of the helicopter?
Well, it's always going in both directions, actually. So sometimes you just have helicopter constraints that require a certain insulation, and sometimes you're only able to reach that with a certain technology. On the other hand, of course, sometimes the requirements for the insulation then also drive the requirement, the design of the helicopter. So, for example, the solution that we showed with the carbon plate was really driven by the requirement to step on the engine deck and to reach this very particular case of dissociating the outgassing and reaching the ignition temperature. So it was possible to do a rather thin protection, but also we needed something robust, and this led to this solution. We would have selected something completely different with different boundary conditions, because as Manuel showed, the properties of carbon as a pure insulating material are really not the best. So yeah, it goes both ways.
Yeah, thanks a lot.
Maybe a comment to add. So
Yeah.
in the end, it goes hand by hand, and what's designed first kind of dictates how the other part will be designed or chosen. So in a really blank sheet approach, then you would kind of go in very parallel to get a global optimum of both the surrounding architecture and the thermal insulation.
There's a more specific question, also addressing the design more or less, I think, is how the connections are designed or constructed, the screws or bolts, and how they influence the fire behavior.
Yeah, so actually for the screws that go through the boundary, in terms of actual fire penetration, so the fire going through that connection, the screw itself forms some kind of labyrinth, so that on its own is pretty much fireproof. But of course, the connections do form some kind of heat bridge that have a local increase in the heat transfer through the protection. And that is something that has to be considered. So there are several possibilities. For example, we also did some tests with a kind of deflector on top of the screw head to protect it from the flame, but in the end, it was sufficient to just increase the thickness of the protection right below the screw head to solve that problem as well.
It's also a question, what's the temperature around the screw on the back side? Yeah? If you have a good insulation on top, then a heat bridge might not be that problem, because through the heat transfer to the surrounding, which is significantly colder than the screw, the overall temperature of this hotspot is reduced to a non-critical level. So it's really depending on many parameters, like Martin said, yeah, screw length, diameter, whether you have a cover on top or not, whether there might be a firewall sealing on top, which forms a kind of insulating charge during the fire event. So yeah, there's no general answer. It depends on many parameters.
That's of course always a good answer. It depends.
It's reality.
Most often it's correct. Yes, maybe we continue with one question to you, Christian, who was posted in the. Sorry. Sorry.
Yeah, you're welcome.
Which is, how do you explain the difference between the BMI and the CE?
So
I assume it reflects a certain. Yeah.
So what we have done there was to put samples in an oven at 250 degree and 300 degree over 4 weeks, and then we have taken them out and we performed ILSS testing again at high temperature to see if we have a certain degradation over time, but as well if we have degradation at high temperature. And as well, we performed tests in this characterization round with samples which were former in dry condition or were saturated with water in wet condition. And what we observed was that first BMI was starting on a higher level with the ILSS values. So maybe there's an improved sizing effect between the different resin system to the carbon fiber. But in the end, both were on a same level, but the BMI, which was saturated before with water, which was tested under wet condition, then aged, and then tested at high temperature, showed a slightly or another. So the cyanide ester was quite better in the performance. Even the performance was quite low. So it's somehow really an kind of worst case scenario which we tested somehow. I don't know if this explains it, or if we should continue the discussion about this.
Yeah, thanks, Christian. If not, I suggest that the person who asks the question makes him or herself aware, and then we can continue. I mean, we don't have a super large amount of questions, so you can also switch on the microphone and ask your question. Thanks. So then I would again like to come back to the Airbus Helicopters colleagues. One of the questions is, you mentioned a couple of certification requirements, CS27 and I don't know the other one. And the question is, which of these requirements could be or should be maybe challenged without affecting the safety? So where's conservatism that could be reduced?
Okay, so in terms of requirements, actually, I think there is not too much margin. It's more about the interpretation and the way the compliance has to be shown. That is a constant matter of discussion with the authorities. So something that has always been discussed is how to take into account the flight loads and which loads to consider in this failure case of having a fire in the engine deck, for example. So this is something where we are always struggling to find a good compromise between being on the safe side, obviously, but also being on a realistic level. And this is also a matter of, let's say, industry-wide discussions. Another thing is that the fire testing requirement is basically using the same kind of burner for all aircraft. And considering the scale, a helicopter is much smaller than, let's say, a commercial airliner. And also the engines are much smaller. So in relation to this engine and the small volume around it, we are talking about a pretty large burner. And that is also something that might be a matter of discussion in the future, to go to a more realistic way to test and to define the fire that has to be sustained, that takes into account this matter of scaling.
I see. So a smaller, more realistic burner would, of course, relax the requirements. You could use less material to still withstand, right, and pass the fire test.
Exactly. So if it is still representing a realistic fire, then we would be able to take a step back on the protection measures.
Yeah, it's Simon here. Yeah, I agree with what you're saying there. This is the point which we didn't get to yesterday, but yeah, we're trying to look at the more realistic scenarios, but how do you do that at a representative level, at a consistency level that makes us all happy? But it's better to have something more representative in the first place. So yeah, I appreciate where you're heading with that thought, and we understand.
We have one question to Hans, who wasn't asked yet so far, coming from the TU Dresden. And the question is, can you say something about the scatter of the results and the scope of the tests? And it's obviously referring to slide 18 of your presentation.
Can you repeat a bit louder, Chris?
Yeah, so the question is, can you say something about the scatter of the results and the scope of the test? And in the question, slide 18 of your presentation is mentioned.
Ah, yeah, this one here. This slide.
I guess, yes.
That's a good question. These results were obtained in collaboration with DLR in Braunschweig. So Martin, who is probably also present.
Yep. Maybe yeah.
Martin, maybe this is something better for you to answer, how you came to these results, because I do not have personally. I don't think we have the scatter data of these results.
Yeah. So can you hear me properly?
Yeah.
Perfect. So I can answer this question. Our initial intention was to compare the BMI with the cyanide ester over temperature. How does it behave? How does the polyester, so phone toughener, interacts with the ILSS strength? And then there was, of course, the opportunity, and Hans came up to also have comparisons of the PFA with different post cures. And then we had this comparison, and also the comparison to a peak thermoplastic material, which is shown here, which we were manufacturing internally. And I can say that the scatter of the, at least of the PFA, is within typical ranges. So I would say 2% standard deviation, similar for all materials. And this was also the case for the cyanide ester and the BMI. It was noticed that the standard deviation within the ILSS was also depending a bit on the temperature level, at least for the cyanide ester. So when we were approaching TGA, the standard deviation changes a bit. I cannot say if it was getting smaller or higher. I must look this up. But it was changing, and this is clearly because the temperature is then another source of uncertainty that comes into the topic. But really, the standard deviations and the uncertainty was close to typical materials. Not any different.
Thank you very much.
Yeah, thank you. As far as I see, we covered all questions asked in the chat so far, so that will give me the chance to ask the questions to Martin Lasak. In the design that you showed, I think it was on slide 8, you mentioned there are fire protection walls, and I'm not an expert on the helicopter. So are these components which are only there to isolate the remaining structure from the large heat, or are they multifunctional in the sense that they also carry load? So are they exposed to mechanical loadings at the same time as they do the insulation?
Yeah, so the green parts visible there, which are the firewalls, are not a part of the primary structure. So they do not carry, let's say, the classic mechanical flight loads from the airframe. However, they also are used to attach the cowlings. So there are some loads coming from the cowlings due to aerodynamic loads that they have to carry, but that's not, let's say, their main function. And the main purpose is really to contain the fire. Could also be a different way to attach the cowlings on top of that. But they are multi-purpose to some degree.
So they do see load, but that's not like the primary purpose, so to say. Yeah.
Yeah. So, and they just do that along the way, basically. So there's no dedicated sizing for each and every part of this firewall assembly. Of course, locally where you have the hinges, you have to take a closer look, but that's just handled by them with their primary function.
So the firewalls, in terms of mechanical requirements, the green ones, they're really different to the engine deck, yeah, which is, as said, a structural part which really needs to carry flight loads in the event of a fire.
Yeah, so this red area is also serving as a kind of firewall, but there is really the secondary function. The primary function is to have a structural element that contains a lot of that transfers a lot of loads, but at the same time it's also needed as a kind of firewall to contain the fire and to segregate the zones.
I see. Okay, yeah, thank you. And maybe one more question, maybe something that I just didn't understand correctly. In the beginning, you said that in some areas, impact damages or damage tolerance constraints cover the fire requirements. It sounded, I wasn't sure if you mean that it's just not the design driver because damage tolerance is the design driver, or is there, because I assume that you would always have to still prove the fire resistance, right?
Yes, of course. So it was not really about impacts in terms of damage tolerance. In the particular case that I had in mind, it was about bird impact. So any part of the helicopter in the front or in an area exposed in forward flight has also a requirement to be bird strike proof, which is rather significant, for example, for the cowlings. So for the cowlings, usually they are sized for aerodynamic loads or for fire containment, obviously. But when they're in the front, they also have to be sized for bird strike, and that is a really massive requirement. And if you size them for that, or if you size the airframe for the flight loads, this usually leads to a laminate that is also fireproof.
See, so it's just not the design driver in these
exactly.
cases, yeah. Christian, you raised your hand. Sorry, I didn't see it immediately.
Yeah, maybe a question as well for you. So you have seen now 2 presentations where we developed some kind of new materials. Do you see any potential for the application in a helicopter? Is there something which is making you interested into it? And what would be next steps in a kind of certification scenario or knowledge gap which are necessary to fill to see if there's a potential?
I mean, we're always interested in new materials, and we did also some similar investigations as you did in the past with all the BMI and cyanide ester and polyimide materials. It's, let's say, maybe you know the Racer demonstrator. Yeah, this is an aircraft which is a demonstrator with like an experimental aircraft with a permit to fly. It's not a serial product, so you don't need full certification. And on these kind of aircraft, it's easier to like get new materials flying, and that's, for example, what we are doing. And this is a big step forward in terms of showing the potential of a material and then like justifying the huge qualification costs we usually face. And this is mostly the issue, since when we are talking about helicopters is low numbers compared to fixed wings. And if we are qualifying a new material, there needs to be kind of business case behind. So, but on the other hand, if there's really an issue we could solve with an innovative material, yeah. So if it's a lever or problem solver, then business case might be a little bit more in the background. Yeah? But just replacing an existing material, which basically would do the same job, maybe with a little bit more of weight, this usually doesn't work out in the end. Yeah? So we would really need to go a big step forward.
Okay, thank you very much also for answering all the questions. The time is up for a discussion round. And I would like again to thank all the presenters for the presentations and also for answering all the questions that we gathered and everybody who asked the questions. We will now have a coffee break or bio break, as we say in the virtual world, and continue with the next session at 11. Tobias, is there anything else to add?
Well, not a lot, but this session will be moderated not by Hans, but by Matthias Kechtermans. But he will take over, so they have agreed on this. And for the next session, yes, we have to keep in mind the timing, really, because there's no room for any extension here to keep sufficient time for discussion. But for now, I think let's enjoy the break and take a refreshment. Yeah, so there's still a minute. I think people will slowly join again. And Matthias, you are here?
Yes, I am here. Can you hear me properly?
Yes, nice and clear.
Okay.
So
Maybe too loud.
no, it's fine. Not too loud at all. That's good. Yeah, I just have the agenda here. I don't know if you'd like to come back to it first and then you can take over.
Yeah.
Is my audio also okay, Tobias?
Yes, Wilco, we can hear you good.
Thank you.
And Thomas, we can see you as well. It works.
Good morning.
Good morning. We can hear you also.
Great.
Right.
Let's start.
Okay, Matthias, please. You can do the moderation. So maybe, yeah, sorry, I may introduce you as well. Sorry. So Matthias Kechtermans is from Transference Chemicals as well, together with Hans. And he will take over the moderation now of this workshop. We've been involved in the SuCoHS program on that material development. And yeah, thanks for giving us the moderation here.
Thank you, Tobias, for the introduction. Okay, so yes, indeed, I'm Matthias Kechtermans from Transference Chemicals. And I have been working in the development of BFA resins, which has been presented in the previous session. And the current session will be involved on the efficient industrialization, with our first speaker being Thomas Ricard of North Thin Ply Technologies in Switzerland. And Thomas has been working at NTPT already since 2011 as a technical director. And he has been in charge of defining and implementing the design and the production software. And he will give a presentation on the implementation of thin ply pre-break materials. Thomas, floor is yours.
Okay. Good morning. Oops, I have to share my screen. I guess you see my screen, guys.
The mountain.
You don't? Do you?
Yes, we see it.
Yes, we see
Oh,
it.
great. Sorry for the little confusion at the very beginning. Hello, good morning. So I'm Thomas Ricard, and I will give you a short presentation about what we do at North Thin Ply Technology and what we did throughout the SuCoHS project, and more generally about the industrialization Simply composite manufacturing. At NTPT, we are committed to deliver high added value materials with improved strength, fatigue, or lightness for demanding applications. And we are a very fully integrated company. So we go from, our work goes from the resin formulation to the pre-preg production to multi-axial preforms and then cured parts. And we went in the structure kind of accidentally because we realized that all the aspects have an effect, and it's quite convenient to be able to tailor the resin while you are defining the preform, for instance, or vice versa. So that's how we became what we are today. We can deliver, and therefore we can deliver our customers and partners at any level, with product at any level of this chain. So UD, preforms, pre-finished part, finished part, whatever. As a SME, because we are quite small, the reactivity and the flexibility are key components of our added value, I would say. And I think in this project, we really noticed that, yeah, it was quite good to have reactive interaction with all different partners. We are also a European company, and the production is entirely in Europe, which these days could be an asset. TPT is, as you can see on this slide, has two sites. The headquarters and R&D are located in Switzerland, and the production is in the south of Poland. And our facility includes pregging lines, ATLs, which I will talk a bit later on, tube making machines, autoclaves, composite shops, and a lot of labs and QC equipment. NTPT is pretty much a R&D and industrialization company. We have a full set of analytical tools to develop our products and to monitor them, to do QC or whatever investigation we might think of for us, ourselves, or for our partners. And we also have some very tight connection with some academic institution to develop things and to be able to answer questions to the people who know the best. We also have a portfolio of products, which is at the bottom of the range, pre-pregs, and it ranges from 330 GSM, which is quite thin, to 300 GSM pre-pregs, which is very standard. And we have, for all of that, we have the quality insurance implemented. It's implemented at industrial scale for resin formulation, for fiber management, for all the aspect of it, and for delivery and all of that. And the process is quite cost effective. So it's not like at lab level where you get a very small amount for a very expensive amount of money. And we are used to manage production. And as I said before, we are very vertically integrated, and so we have all the things we need to produce. So what's the difference? What's the difference between conventional ply and thin ply? Basically, in conventional ply, the toes of fiber remains as toe, and it results to resin-rich areas. While in thin ply, we basically spread the toes into yarns. Therefore, in the microstructure, you cannot see the structures of toes anymore, and the yarns are spread like spaghettis on a table. And therefore, the connection between the various plies in the structure is much closer, and there is much less resin, much smaller, I would say, resin-rich areas. And as the cracks tend to propagate in the region, in the big zones of resins, it tends to reduce the crack propagation dramatically. And yes, exactly. So the benefits of that, and therefore it brings several benefits in terms of mechanical properties. So, for instance, the 0-degree compression can be improved up to 20% when we go from 300 GSM to 30 GSM. And this was documented by following some research done at EPFL. Another very important aspect is for multi-axial testing, such like in-plane shear and or quasi-iso tensile tests. As you can see on the pictures below, the cracks are much neater. And when we are on thinner plies, as the strength of the composites tends to reach the strength of the fiber, because there is no crack, much less crack in the resin. Therefore, we kind of achieve the intrinsic strength of the fibers. And the other very important aspect, which is very correlated to the previous one, is the fatigue resistance, which is improved dramatically as the fiber, the ply fiber RL weight decreases. A lot more tests have been done, but I will not show all of them on this presentation. And all of that results to an improved design space, because as the bricks, the quantum in the structure gets smaller, obviously there is a lot more possible combination, and therefore the designer has some new choices open to him to design the structure he has to design. So, as I said before, yeah, the process is quite versatile, and in terms of fiber, we can process pretty much any kind of high-performance fibers, from carbon, pan or pitch even, glass, quartz, aramide, or any other. And depending on the kind of fiber, we can, and of the grade of the fiber, the thickness of the tape we can make can vary, but basically, as you can see on the number, we can go quite low. In terms of resin, actually we've been, over the years and over the project, we've been developing a full range of resin for various applications. The latest today is obviously the TP164, which is the one developed within the SuCoHS project. As Christian explained earlier, this product, designed for aerospace application, has amazing properties, both mechanically and thermally. Having light ply is good. However, now you have to, as you have a lot more layers to lay, it's very important to be able to lay down, otherwise the production cost will go through the roof. Therefore, in parallel of developing pre-preg, we developed ATL machines, and we made the choice to work in 2D, so to have flat tables, which is interesting because it makes the technology much more cost effective, very efficient, and extremely versatile, as no molds are required. And furthermore, thin plies are, there is a lot of application that require thin plies which are flat. But we are not limited to flat, obviously. And we also believe that a mix of thin ply and other materials, such like woven or heavier ply, is an optimum design. We do not claim that thin ply should be used everywhere. And the preform can be delivered either at our client, or we can use them to make finished products. So now TPT and SuCoHS, what's happened? So quite a lot actually. As Christian Bromer explained earlier this morning, with the SuCoHS project, high temperature and high performance ultralight prepreg were developed for aerospace application. The collaboration was extremely successful. As Christian and his team were designing formulation, we were doing small batches of it to assess the product production friendliness and the product performance. I think dozens of iterations were made before achieving the final product. And the features of this product are listed here. And we managed to increase the toughness by some additives, and we can cure at standard autoclave temperature. It has very good thermal properties, and it's fire resistant. And of course, it's thin ply compatible because it was designed to be like that, and it can be processed on AFP, which is actually quite a challenge because AFP do not like tackiness. And in terms of readiness, as we went through some benchmarks, we had to produce some reasonably big quantities of this product. So the product, I would say, is ready at semi-industrial level. However, the process is fully defined for higher production, higher volume production, and the quality control is in place if we have to go for big production in the coming months or years, if a partner decides to follow this route. So I think from my side, that's pretty much it. I would like to thank you for your attention, and if you have some questions, I would be very happy to answer or to discuss any aspect of the project.
Okay, thank you very much, Thomas, for the interesting presentation. It was well within time, so we always appreciate that. Since there are no immediate questions, I suppose.
Yeah, go ahead. Sorry. No, go ahead.
No, yeah, since there are no immediate questions, I suppose to hold any potential questions which are coming the upcoming presentations to the discussion period afterwards.
Okay.
And we can proceed now with the presentation of Wilco.
Okay.
So Wilco, Wilco has been working at the Royal Netherlands Aerospace Center for already quite some time, since 1998, if I'm not mistaken. And he has been working there as a senior R&D engineer, where he managed several research programs related to the development and the automation of structural components. And he has been a central figure in the entire project with the AFP processing. We've already shown a lot of his work, but I'm sure that he can still provide some more information on the automated fiber placement. Wilco, please go ahead.
Thanks a lot, Matthias, for the introduction. Can you hear me?
Yes.
Okay, very good. That's good news. Yes, working at the Netherlands Aerospace Center, NLR, and a lot of work was already shown. So I have only 15 minutes, so please let me try to bring in a nutshell what we did for this program. Yeah, it's always good, of course, to work with partners that are searching for, let's say, new technologies, new opportunities to work together. As we see it at NLR, is that the innovation gap is always there. So people have nice ideas, but don't know how to bring it to the, let's say, to the shop floor. So what we try to do is, of course, with our experience, to help people, to bring their ideas to the manufacturing, to the shop floor. And that helps us also, to stay innovative and to find new solutions to do things that we never did before. And I think this is a pretty good example about things that we have not done before. So together with the use case partners, it was really great to, and also with the sensor partners, it was great to find new solutions. So let's please start to highlight per use case. So it was already shown yesterday, but just briefly. First of all, on the right side, you can see already the results of the very nice demonstrator. What we had to do here is, of course, to do fiber steered stiffeners on a curved skin. That was quite new for us. And Collins Aerospace came with this question, and together we checked feasibility of the concept. And with the experience we had before, and with some trials, we were confident to work it out this way. What is not really new but interesting is to have ply architectures with multiple orientations. If you can see here on the right side, that you see some kind of waviness here. So we're going from 0 degree up to 90 degree in one ply, and all the other plies you have to cook for the same thing as well. So fiber steering is involved over there. AFP on woven fabric, not very special, but it was in combination with the stiffness also again new for us. And obviously, as already explained by Hans, the PFA material for AFP. That was also challenging to find solutions for that. Going to the next use case, taking some water, sorry. Yeah, so during the lunch break, after the lunch break, we will focus a little bit more on this use case, but very briefly in this slide. There was also some challenges absolutely here for this use case. First of all, as you see on the right side, we discussed if there were possibilities to have fully integrated blade stiffeners for the panel. So it's not a co-cured, let's say T-shaped stiffener or co-bonded, but it is fully integrated into the panel. That was one thing to work out together. Also here, of course, AFP together with the cyanide ester system. And then also with thin ply technologies, that was also new for us to have thin plies for AFP to see if it is feasible. What was also very new in this for this use case was the embedded optical fiber with firebrand grade sensors from Photon First. And we decided, to position these optical fibers by fire placement. So we changed the fire placement machine to be able to position optical fibers with the machine. Come back later to that. And obviously to find a way to get access to the fibers who are absolutely embedded into a panel. So if you trim the panel, that you don't cut the fibers. It's not very helpful, of course. As already explained yesterday, quite in detail by Daniel. So also for this shape, it was challenging. So not only the concave shape of the nacelle part, but especially the cutouts in the honeycomb material. So the ramps must be followed by a machine, and later on in the presentation you see a movie. Exactly, you see that it's right on the limit of what we can do with our machine. One of the things to consider, come back to that also later during this presentation, is how to fixate the mold on our horizontal spindle, and also the strategies that you have to do during the simulation of AFP. to be sure that you can reach each area of the component and to to let the machine do smooth movements, and that all areas can be reached. AFP process window on core material. You can imagine that if you directly fireplace on, let's say, a solid mold, that the amount of heat that flows through, let's say, the substrate and the mold is different compared to when you have a honeycomb shape. So the mass of the substrate directly underneath the roller is different. So the process window will also be different. And for sure, in terms of accuracy for let's say, the fiber orientations, automatic sectioning is one of the things to consider for, let's say, a good simulation of the fire placement program. So not only the use case partners had some questions, but also our sensor partners. We had 3 in this program. Synthesites, PhotoFirst, and Apodius from Hexagon. As explained by Tobias yesterday, unfortunately, Apodius is not existing anymore, but they had really developed a great technology, which will briefly be shown also in this presentation. So also from the sensor partners, we received questions if we could, incorporate their system into the products and also into the processes. And I think we had really a great group of people, to get these things done. So there were many ingredients to come with the menu with nice receipts, and I think, yeah, we were quite good, successful as a complete team, as a whole consortium. So why fire placement? Because fire placement was selected for all the 3 concepts. I think everybody knows tape layering. That's more for the conventional way of layup. So the precision rate is very high, but limitation is that if the the shapes becomes a little bit more complex, then you get wrinkles and other type of effects. So fire placement is helpful. And please let me show you the movie for the people that are not so familiar with fire placement yet. So what are the difference is that you have several narrow tapes beside each other that will be positioned on the substrate. Here you can see that each time, a new tape comes up to close gaps over here. So it's not only closing gaps, to be more precise and to have more opportunities and possibilities to do ply architectures, but also here, as you can see, you can steer and you can define to use many tapes or only single tapes to close certain areas. So it's a quite flexible system to drape material on top of the substrate. Here you can see also an example of fiber steering. You can also work out a method that if you have a conical shape, let's say a complete conical shape, that you fireplace the whole area without cutting any fiber. So okay, that's about fire placement. I get a message to switch off the virtual background. That's what I did. So let's go for the next slide. Yes, what we did also in the past is, and what also can be done by fire placement is the grid structure that you see here on the left. Sorry, on the right. On the left side, you see the conical shape. And what we did in this example is to reduce the amount of traditional stiffness on the inside of the shell, and then find solutions for post buckling by smart overlapping. So this is an integrated stiffener that was given shape by smart overlapping fibers in plies and then gain, let's say, thickness development. Yeah, when working with new materials and with new mold concepts, it's always the case, to find a process window for this new combination. So working with composite molds or with metal molds, you can imagine that the first layer and the second and after the third will be different in terms of process window development. So you have always, it's a matter of finding the right fire placement, speed, and combination. It's a combination of all these aspects. So the amount of heat, that's quite obvious. The compression force, this is a thing because there is really a force on the roller. It's not that you can define pressure, but it's really a force. Obviously the mold temperature. So for some materials you have to regulate mold temperature. Real unit temperature, as you see here, must be in what is it, a regulated chamber where you arrange the right humidity and so on to find sufficient tackiness. Tackiness is the thing to find while finding the right process window. FP head temperature, so inside the head you have all kinds of cutters and stuff and guides that should not get any pollution or contaminations, you know, from the tapes itself, because you will get problems over here during fire placement. And even room humidity is very important for finding the right tackiness for the material. So having a controlled room is extremely helpful for some materials. Yeah, some challenges sometimes. So sometimes we see, let's say, very bad results as a deposition on a mold. But yeah, sometimes we receive already materials with some errors. So it's challenging to find, let's say, a complete chain where every link has the required quality. So you need for the whole chain, every step, the right quality to end up with, let's say, a high accurate fire placement process. This was already mentioned by Hans, so maybe not too much go in detail for this. Yes, the integration of optical fibers by fire placement. What you can see here on the top left is that one of the 8 toes, one of the guides was selected, you know, to incorporate an optical fiber. So cutters and everything can be used to cut the optical fiber and to, you know, to make a longer path. To have excess length for the optical fiber. What we did is for in the material guide, make special guides for the optical fiber in a conical way. So here you have the feed rollers and also the cutters that need, let's say, separately guides to control the feed through of the optical fiber. Later on during the, let's say after the lunch break, I will show you some videos how it's been done. Yes, looking at the right picture, there were challenges, of course, for making crossovers in the stiffeners. It was already explained yesterday by Andrew. So there are 2 types. You have a waving out cross and a straight cross. For the waving out, yeah, of course the fibers are not straight, but the thickness development in the middle is let's say twice as well as that you have thickness development here twice. However, in the transition area, there is let's say another thickness development. There are some areas that only have a single thickness, while the other have a double material. So there are ways to do it, but the wave out across is quite complex. But you can see here an example that that it is possible. So we did it in the past. This is the more easy way to do across. So here let's say the plus 45s are cut, and for the next ply, obviously, you know, the minus 45s will be cut, and then you will have a straight fiber on the 45 degree direction. Also fiber steering, that's also what we did in the past. So what is the limit? What is the minimum radius that you have to account for? So we did some tests in the past, and we know where the limitations are. So what kind of minimum radius you need to stay out of too much scatter in results. So that was helpful also to work out you know, the Collins Aerospace use case, because we already knew what the minimum radius was to consider. So that was very helpful, this information. Yeah, so here let's say the multiple orientations again. So in one ply you have 0 degree and 90 degree. Obviously together with fiber steering and the underlaying let's say plies, you have to take into account, you know, that you don't have to do some special things to end up with the right layup.
Sorry, Wilco, time is over. Could you please sum up?
Yes. I have to speed up.
Time is already exceeded by 2 minutes.
Oh, sorry. Okay, I will speed up. Okay, I think there are some movies that show how difficult it is to be in, you know, to have a feasible concept for this shape. It will be shown in the video later on, short videos. So here we have the remaining is the 3 videos of the 3 use cases. So starting with the one from Collins Aerospace, you see here that the steering is very helpful to you know, to make the layup and also to create the you know, the steered stiffness on the substrate. Yeah, experience from the past was very helpful, and we used some of the technologies, but improved it, you know, to have it feasible for also for curved shapes. Going to the next one. Here we see the Apodius system working. I think in the next view you can see it on this on the back side now. This is the skin preparation for the ANOVA use case. Yeah, Apodius system is really a great system. So here you see the camera and the lightning making pictures during fire placement, and in the next view you see how it works. So with the thin plies we had some more gaps as yeah, as you see normally by fire placement, so that was ideal for proving you know, the capabilities of the system of Apodius. So online monitoring is there, and all this information will directly be forwarded to the database. So it's a really good system to build up a track record and to recognize defects if any. This one it's also a short video. It's already shown yesterday by Daniel. This is a couple of layers further in the process. Within a couple of seconds, you see how the head is moving inside, you know, the cavity of the honeycomb material. So I think it will. You can see here that it just fits inside the shape. And it is really, yeah. You need a small machine like we have, you know, to make a feasible concept for this type of shapes. So thanks for your attention. That was my presentation.
Okay, thank you very much, Wilco. Yeah, I didn't want to interrupt you because I noticed that there weren't a lot of questions yet in the chat, so I figured you can give us some additional time in the presentation because you've done a lot of work, and it's difficult to show that in 15 minutes. We know that, but we will continue with the discussion again after the presentation of Nikos. So if there is anyone who is wants to ask a question to Wilco or Thomas, please mention it in the chat or in the Slido system. So the third presentation is from Dr. Nikos Pantelidis from Synthesites in Belgium. And Nikos started his career as a researcher in the advanced composite manufacturing before he created Synthesites, which is currently pioneering the intelligent process monitoring for composite manufacturing. So Nikos, we've seen you already in quite a lot of pictures. So please share with us your presentation.
Thank you, Matthias, for the introduction. Can you hear me well?
Yes, we can hear you.
Okay, that's great. So yes, today I'm going to talk about our contribution in SuCoHS project. Due to the limited time, I will just go through. I will just touch some of our work, and I will focus just on the demonstrator of the Spirit nacelle IFS component. And also I will stress more about our work about online TG and viscosity monitoring. Just a few words about our technology. Is based basically on the measurement of temperature and electrical resistance of the resin. And we are providing a full, complete suite of a solution for optimizing and control composite processing in general. From I would say from RTM and infusion all the way to autoclave manufacturing. We have the optimal system, which is more focused on the curing. OptiFlow system, which is more about infusion and RTM for resin arrival and temperature. And we have developed our own sensors, durable sensors, disposable sensors, and all the kind of sensors that could, let's say, installed in a mold or in a tool and just measure the necessary properties during manufacturing. Then we have also developed software to, let's say, get all the measurements in real time from the systems and the sensors and transform them to useful properties that, let's say, the composite manufacturer would need, such as gas resistant temperature, viscosity, or also mixing ratio, resin quality, and other useful properties that could help really optimizing the process either offline or in real time. And of course, the idea is to close the loop and have a closed loop feedback control from the monitoring systems to the measurements, from the measurements to let's say useful properties, because in practice, most of the composite manufacturers are not interested about the electrical properties of the resins, but they are interested about, let's say, the viscosity and the curing. So this is an important step to reach, let's say, composite manufacturers and not to stay in, to remain at the lab scale of process monitoring. And then at the end, in order to, let's say, close the loop and have a real-time control, there should be, let's say, a scenario and some algorithms in order to decide about the control actions and feed these control actions to either the injection machine, the temperature controllers, the oven, and the autoclaves. We are lucky that we are working with leaders in composite manufacturing. We have been working both in aerospace and also a lot in wind energy in this intelligent process monitoring, and we are also working with leading R&D centers, mainly in Europe, in order to deliver, to further develop these technologies and deliver them and provide them to the composite manufacturers. Now, a few words about the technology that we have used, especially within SuCoHS. We have used the optimal system, which is a system that we have developed since 10 years now, and we have constantly, let's say, improving. The system, the monitoring unit measures the electrical resistance and the temperature of the resin. Especially for the electrical resistance, this is a quite unique system because we have used it. I mean, of course, it works perfectly within a lab environment, but we have used it extensively in the shop floor, in production, and not only in aerospace, of course, but also a lot in wind energy, where there the conditions, the production conditions are very different. And we have seen a very amazing robustness of the system and of the measurements. So it's a quite reliable solution, and this has been what was done in SuCoHS was connected to durable sensors, disposable sensors, in order to come up with the right measurements. So within SuCoHS, we have further developed both the durable sensors and the disposable sensors. The durable sensors mainly to work because of the problem of dielectrics. It's well known that if you have a sensor in direct contact with carbon fiber, it just have a short circuit and it cannot work. So we have this was a very important aspect within SuCoHS because we only had carbon fiber prepregs. So it was important to develop a solution that would work with carbon fiber without the need of having without the fear that there would be a problem during the measurements. Also, we have further increased the capability of disposable sensor in order to be used at higher temperature, higher than 200. Furthermore, it was important especially for the demonstrators to develop a system, non-intrusive cure monitoring system that could be used with the autoclave without the need of having what we call feed-through glands and cables in the autoclave and in the mold. This was very critical, especially for the for the nacelle IFS demonstrator. And last but not least, we have developed a series of online resin state systems for the different for the various resins that we have used within SuCoHS. Oops, sorry. So the Cure simulator, the Cure simulator came actually accidentally within SuCoHS because it was obvious that after some point especially for the nacelle demonstrator, we would not have the chance to install a feed-through gland in the autoclave that was going to be cured. So we started developing a concept that could be utilized without having a sensor, actually an actual sensor, cure sensor in the mold. So what we have developed, and you will see the results later, is a system that could copy in real time the temperature that was measured close to the product or very close to the product inside the autoclave, and transfer the measurement outside, and actually applying this temperature in a cure sensor and with the prepreg that was actually cured inside the autoclave. This was quite challenging. It's not perhaps as easy as it sounds, because we had to ensure that also our online TG software was working at the same accuracy level. So within SuCoHS, we have worked with several new for us resins. So we were always anxious to try them and see that the monitoring system and the sensors were working well. The first one was the Sinatester resin that was developed by FHNW. You can see just a graph with two trials we did in NLR autoclave, and you can see the very good repeatability of the measurements, and also the good, let's say, repeatability of the online TG that was provided during processing. Furthermore, we worked a lot with the PFA resin from TFC that was presented before. The PFA has a unique, let's say, property that generates some moisture during the first part of the curing. So that was challenging for our sensors, but finally we managed to work well with this system, and we have produced some very good results. Also, we worked with the let's say the baseline resins and prepregs that the end users, our partners, were using because it was very very important, let's say, to have a global view with respect to cure monitoring and TG evolution. Last but not least, we have also installed the system. You can see on the left, we worked very closely with NLR, and you can see you can see the feed through and the wiring that was installed in their autoclave, and also on the left hand side below the bottom, you can see the picture from the oven that was used. Then we used the Cure simulator with Spirit's autoclave in Belfast, on the top right, and also Cure simulator at Fokker installation where we did the demonstrator. Here you don't see a picture of FHNW, but FHNW also worked with our Cure simulator in order to use it for the cure monitoring of the demonstrator of AirNova. Now, a few words about the procedure, how we, let's say, calibrate. We say calibrate, but it's not really calibration. It's how we developed the ORS software in order to provide the online TG for a specific resin. So this is the case of Spirit demonstrator, and we have worked with them in order to develop this ORS system for this specific resin. You can see here that we ran several trials at different temperatures, curing temperatures, 177, 190, and 170, just to feel comfortable with the resin with the prepreg, and just to check the, let's say, the repeatability of the measurements. Also, for the development of the Q simulator, we did a lot of trials and development in order to ensure that the Q simulator could produce the same level of measurements as in the tool, as the sensor was at the tool. And you can see how well the two Q cycles are correlated, one in the mold and one in the Q simulator. And also what we did a lot, especially also with NLR, is to develop, let's say, a system in order to secure the pre-preg on the simulator in the right way. And this was very important in order to provide this to Spirit, so we were sure that everything was working well. So for the calibration, we produced DMA coupons that were provided to Spirit, and Spirit measured them, measured the TG, and as you can see here, the first version of the calibration, you can see that the online TG for different temperatures, 170, 177, and 190, correlate very well with the TG that was provided by Spirit. This was the first phase of the calibration. And then the second phase.
Nico, sorry to interrupt you. You have also exceeded the timing. Could you please speed
Yeah.
up?
Yeah, I think I have.
Thank you. No problem.
Slides. So you can see here that when we shift this to shift the Q simulator to Spirit, you can see the trials. They perform 5 curings, and you can see how well the TG provided afterwards, measured by DMA, was correlated to the TG that was provided online by the ORA system. And actually, what was obvious is that if Spirit could increase the curing temperature by 14 degrees, so from 177 to 191, they could save 50% of the curing time. Finally, for the demonstrator, we worked a lot with GK Infoker, who offered to run this demonstrator. And you can see here the pictures during the trial, where we managed also to have the online TG. But of course, the Q cycle didn't change based on that. For conclusions, the new dielectric sensor eliminates the need for additional glass fabric to monitor the curing. For carbon fiber structures, new algorithms were developed to provide the online TG for modified cyanoester resins for PFA and for BMI. All monitoring technologies were installed and tested successfully at NLR, FHNW, and Spirit Infoker. The Q simulator can eliminate completely the need for mold modifications and wiring in the autoclave, still providing the same level of cure information online. And what we have seen is that the significant cycle time reduction was achieved in all cases, leading to reduction of energy, cost reduction, of course, and productivity increase, always ensuring curing quality. And that's from my side. Thank you for your attention.
Okay, thank you very much, Nikos, for the presentation. And I would like to also thank Wilco and Thomas again for their clear explanation on the work performed in the SuCoHS project. So there are a few questions that have been asked in the chat and in the Slido system. So the first one was directed to Thomas. What would be the limits in the terms of the volume of the production of the thin ply material?
For the product developed for SuCoHS or in general?
I would suppose in general, but you can also specify it for the SuCoHS project.
It's basically we have 2 lines of production, and these 2 lines can work at like let's say rough term 5 meters per minute, and they are 300 and 400 meter wide, millimeter, sorry, wide. So you could, yeah, we could do the math, but it's that's the order of magnitude. So we can talk that's the order of magnitude. So we can do several hundred of we do batches of several hundred of kilos with no problem, and we or even tons. Yep.
Okay, so in addition to that, perhaps a small question from myself. You mentioned you gain significant mechanical performance by using the thin ply materials.
Yes.
Say we turn the question around and you aim for the same mechanical performance. How would that translate into cost reduction, perhaps, of the composite material? Because we've noticed from the life cycle analysis that carbon fiber has a large influence. Will the 20% increase in mechanical performance translate itself in a large enough cost reduction, perhaps?
It depends what you do with your mechanical performance. If you decide to improve your safety, basically the part will be the same weight. Therefore, you do not save any material. But if you go for lighter parts, you save on the material cost, obviously. However, the breaking the 1 gram of thin ply is a bit more expensive than 1 gram of heavier ply, because the line basically runs at the same speed but has less throughput. So that's it. Yes. So yeah, it all depends. I think the key aspect is to say that the design space is increased, and then it's up for the designer or the marketing people or whoever to decide what we want to do within this design space. I think that, yeah.
Yeah. Okay. Thank you. That was a good answer.
And basically, people chasing price usually do not go for thinner ply, but I think the thin ply tend to scare people because they say, oh, it would be too expensive for me, and my structure do not require this, thin ply everywhere. But we think the right approach is to put thin ply where it's required, and to stagger it at the transition with heavier plies, and which is especially true in aerospace. Yep.
Okay.
Over.
Thank you. So the next question was directed to Wilco. There are a few questions directed to Wilco, some small ones, maybe a larger one. The first one, or the most popular one, being, is there any special arrangement to deal with the egress point of the embedded fibers?
Yeah, that is quite a big story behind, I think. So the reason for embedded fibers that was already discussed, obviously, from the beginning. And one of the things that popped up then was, to think about circular composites already. So if you want to give composite parts a longer life, how to deal with maintenance and how to deal with repairs. So I think that was one of the reasons to try to have embedded fibers in parts. After the lunch break, Photon First will give a presentation, and there will also be a few slides from my colleague Frank Groteman in this presentation, and he will explain how optical fibers with fiberbrick sensors can help, to find what is it, the impact size and location during operation. So I think that that's one of the reasons, to want to have embedded fibers inside parts. And secondary, there was a reason that during cure cycle to have already embedded systems involved. To check for resin shrinkage issues, temperatures, maybe on special locations. So it could be a combination of facts while using exactly the same fibers with fiberbrick grade sensors. So that was the reason. The other thing is that everybody knows that if you put optical fibers inside the laminate and you cure it, then afterwards you can, in most cases, especially for thin parts, still see the imprint of the fiber itself. So it gives undulations to the fibers and all kinds of stuff. So for this project, the meaning was to have a fully integrated fiber into one ply. So then you have to, to go for UD tapes, and then the thickness of one ply should be, let's say, larger than the diameter of the optical fiber. So that was also a reason to, to go for a fully embedded fiber solution. And thinking about all these, let's say, requests or let's say questions from the partners, we thought, okay, could it be feasible to make it part of the manufacturing system? So in this example, fire placement. So could we reserve space for positioning of optical fibers during fire placement? Then you can obviously incorporate them in each ply you want to do, and also close the gaps in between the fibers with fire placement. So that was the reason for the whole thing.
Okay, so in addition to that, there was also a question how, while embedding the fibers by automated fiber placement, how do you avoid breaking them?
Yeah, that's a good one. Because only looking at the feed rollers, and I will come to in my presentation after lunch break, we'll show you a video. But yeah, it could be some kind of what we call here a shredder, that the fiber comes out in pieces. But what we learned from experience, also together with Photon First, that if you put tension on the fiber, it's really strong. The only thing is that if you kink it or you bend it into a small radius, then it's quite brittle and sensitive for to be broken. But okay, if you deal with it in the right way, it is absolutely feasible, and I will show it later on in video after the lunch break.
Okay, we're looking forward to that video. So a final question, Wilco. If it's possible to confirm if the AFP was used only to create, or was AFP in itself was used to create the stiffeners, or to reinforce already existing stiffeners by placing AFP tapes on top of those existing stiffeners.
Yeah, no, so the grid system that I showed in my presentation, and also the Collins Aerospace use case, that was let's say a completely monolithic structure. So from the bottom up to the top, we did it with fire placement.
Yeah. Okay. And finally, the question arises: which heating mechanism was used during the AFP placement?
Yeah, so our machine, with our machine, we can do the dry fibers, the thermoplastic materials, and the thermoset materials. For the thermoset, we have an infrared heater on the head, so you see the light, that's the infrared. For the thermoplastic and the dry fiber systems, we have another. It is a laser equipment that is capable to bring in more heat if needed. So, but for the thermosets, in most cases, the infrared is sufficient, and even for some thermosets, it's even without infrared, it is possible. Looking at mold temperatures, what we have in our fire placement room available is a table that can be electrical heated. So, and we can just set the temperature, and that's helpful for doing trials with new materials to find process windows that also incorporates a certain, let's say, temperature of the table itself. So once we know that temperature of the mold is necessary, so for some systems it is necessary to receive or to gain sufficient tackiness. So then we know also what the requests are for the for the design of the mold. So we start always on flat on the table, and then once we know that it's absolutely necessary to find sufficient tackiness and to heat up the table, then or the mold, then we at least know what to do.
Okay, thank you very much.
Okay.
Nikos, there has also been a question asked in the chat for you. So the question, I assume that it's based on one of the tables in your presentation or one of the graphs in your presentation, is why there is never a TG value shown below 120 degrees C.
Yeah, I think this is actually a very, very good question. The explanation is there are two explanations. The first one is that our algorithm, the TG algorithm, starts to let's say estimate TG after gelation. Before gelation, it's just is focusing on viscosity, because before gelation viscosity is more important, and then after gelation, it's the buildup of TG. And also the second explanation is that in this case, for aerospace applications, we focused our calibration, let's say, towards the end of curing. So we can expect that below some specific TG, let's say, for example, 150, the estimation are not so accurate. And in any case, we have not let's say checked them against measurements like DMA. So that's why you see this all the curves starting at 120, but this is actually, let's say, an artifact, I would say. So it's better to focus. And in this case, it's the accurate results is after over 150 degrees C. But we have worked a lot with especially in wind energy, because there it's much more important, and to work a lot with let's say uncuring, not fully cured resins, and there we have also seen that calibrating, focusing on the area, let's say, of mid cure, it's also possible and also very accurate. But so it's a matter of where the customer needs to focus the calibration.
Okay, thank you. Tobias, you raised your hand.
Yes, thanks. Since there's still time, I have a question for Nikos indeed. Nikos, you have shown the background why you have created that Cure simulator, and I was wondering now for the further exploitation if there's also a good exploitation, because maybe a Cure sensor itself, the hardware sensor, might not be installed everywhere in very complex shaped composites. So in terms of integrating into a composite layup or even in a complex tooling. So would it be even an exploitation for such critical areas in terms of quality control?
Actually, I hope so. It was very interesting to see that GKN Fokker during our our trials, our demonstrator show a lot of interest for this. So I would expect that yes, it doesn't solve it doesn't solve all the problems, but for sure it helps cure monitoring being adopted much easier, especially for people that and I think in aerospace there are many of them that think that they cannot touch the tool or the autoclave. So in this case, with the Q simulator, you can combine both. So I think I would expect that this would be a nice, a good idea to use. I can say that we have already using this in wind energy, especially for monitoring the curing of the adhesive in the bond line. So by just having the measurement from the bond line, we can reproduce the curing of the adhesive at the Q simulator without actually touching a lot the bond line. So this is for us. It's a good let's say good way to exploit the results of the Q simulator also in other applications than aerospace.
Yeah, thank you.
Okay, so thank you very much. Tobias, perhaps room for one final question before going into the lunch break. If there is anyone from the audience who still wants to ask a question to any of the three speakers, you can unmute yourself and please ask it. Okay, if there is no one, so maybe a final question from me to Nikos. I remember yesterday there was a question being asked during one of the presentations of the use case partners. If it was only the DG monitoring which was being performed continuously, or if this can be elaborated to other properties, such as, for example, an online monitoring of mechanical performance, or mechanical properties, if the calibration can be done accordingly.
Frankly, we have never tried to calibrate against mechanical properties because DG is, let's say, the main indicator for composite manufacturers about the, let's say, the level of curing. And that's why we have focused mainly on TG. Sometimes we can, we can transform TG to degree of cure. But I think what is also important, perhaps not so much in prepregs, but perhaps also in prepregs, is the viscosity. So during, let's say, the first phase, when resin is still liquid, with our system, you can check the viscosity and the evolution of viscosity. And we have also worked with NLR a lot in this area. We have seen that you can estimate the viscosity online using the same tools. And also you can see the aging of the resin, which sometimes in aerospace is also very important and critical. So there are many properties that you can relate to electrical resistance and temperature, but we have never tried, to correlate directly the mechanical properties of the resin.
Okay, thank you. So there has been a final question in the chat. I don't know if it is okay to still answer it.
Yep. I think so, Monsieur Bechtel. Yeah.
Yes. So Nikos, the question was, is there any issue with the pressure being applied on the sensor when it is introduced into the composite material?
the pressure applied on the sensor.
Pressure applied, I assume that pressure applied during the curing phase, either by the vacuum bag curing or by the autoclave pressure.
The autoclave pressure, or perhaps also the pressure from when the mold is clamping. But in any case, we never have any issues with the pressure either. I mean, we have NCC has used our sensors for pressures up to 200 bar compression, high pressure RTM without any issues. So we never had any issues with with pressure on the sensor.
Yeah, and if the question maybe is related to optical fibers, you know, within 15 minutes, I will do a quick sandwich, but then I'll explain a little bit more about that. So, and also about the egress point, maybe it was related to, you know, how to get access to the fiber. That will also be explained in my presentation after the lunch break.
Okay, then I would like to thank every presenter for their clear explanation in the questions and again for their presentation. And I think we can conclude this session and go into the lunch break. If that is okay with you, Tobias.
Yes, thanks a lot for having the moderation here. And I'm sorry if I'm being rude to interrupt speaking us, especially Wilco now. So I'm hoping that you will have time for attending one of the tours either now during the lunch break or in the afternoon. As I said, it will be twice the same story. And so yeah, I'm happy to speak to you in a few minutes again. Enjoy your lunch break.
So can you hear me again?
Yes, we can hear you.
Yes.
Ah, perfect. This was again the issue that we had in our talks. When you switch on your presentation, then the audio changes. Okay, so should we give it a start? So welcome everybody to the DLR Institute of Composite Structures and welcome to our virtual lab tour here. My name is Martin Liebisch. I'm the responsible research associate here in the thermomechanical test facility, or also short Thermex facility. I'm wearing a headset. If there is any audio issue or any problem with the video, my colleague Dominika or Tobias will let me know. Keep in mind there's at a few cameras there's 1 second or 1.5 second delay. That's typical due to the USB connection. If you have questions, please again write them into the chat and we will have a discussion afterwards. So, as we already heard, the SuCoHS project discusses composite structures under high thermomechanical load conditions and also within fire scenarios. Such high thermal load conditions are quite a challenge for the materials and also for the structures. The plastic material properties soften, and so do the composite properties. The thermal load introduction into the structure produces thermal gradients within the structure and thus also thermal deformation. To tackle those challenges, we have investigated a few different options within the project. One was the material solution, which we have heard before, a cyanide ester that can withstand higher temperatures with equal autoclave using equal autoclave curing temperature. Second option that we have investigated was to use enhanced analysis methods that are usable to exploit higher surface temperatures compared to the present ones. This will be part of a presentation on this afternoon. However, all of those new developments require a certain experimental validation. This is a tough requirement. About such experimental validation on structural scale, we will inform you within this lab tour. We have already tested one of those structural tests. Here you can see a stiffened panel, as Wilco already showed before. We have already tested once within the project. A second one is lying here, ready for sensor installation on the table. How we will install those sensors and how we produce the structural test will be part of our lab tour here at the Thermex facility. before we go into this lab tour, I want to hand over again to Wilco, who explains some more details how we manufactured those test articles here. So Wilco, the stage is yours.
Thanks a lot, Martin. So let me share my screen again. So 1 minute. Share. So hopefully it works again. So yes, so in this presentation, or let's say virtual lab tour, we will focus a bit more on the ANOVA use case. Yeah, so just let's start with that. Normal-wise, if we would have, you know, a meeting at NLR, we would have shown you around and show you our facilities. I think, you know, in real life, it's always the best way to show what our capabilities are. But since we have a virtual one, and since we have a lot of movies available and information on the internet, I propose, you know, if you are interested to have a look at our website. On YouTube, we have an our media channel that shows a lot of videos also with our equipment, and even we have a report page. And if you search on Composite, you will find a lot of papers there from investigations that we did in the past. So just to give you this quick information, if you are interested, there is a lot to find on the internet. Yes, so the three use cases again, and this time we will focus more on the middle one, so the ANOVA use case. For the next slide, so in concept, what we did is, you know, discussing together how to create a panel with blade stiffeners, and which are the options, and what could be a reason, you know, to find fully integrated blade stiffeners. We had some experience already from the past. Some tooling was already available, so that was the reason, you know, to try to do such a panel also with decided as the system. So in principle, it is a skin that will be fiber placed, and it will also have integrated optical sensors. We make a U-shapes by hot forming. We'll show you later on in the movie. And then these U-shapes will be connected to each other, and that will, you know, complete the whole concept. So here you see a little bit the tooling. So more in detail, the red part that you see here is the skin, is relatively thick. So our calculation guys came up with the thicknesses that you see here on the screen in concept. So the blue part is, you know, the hot formed shape. It's only a couple of plies. The gray part is the cold plate, and the yellow part is the filler that we made by UD materials, and also with designed as the system. The green part is just let's say a laminate that is coupled in between the blue parts, and that's the way how you know, how to integrate this blade stiffener. So from the past, we had pretty good experience with this way of working. So that was also what we expected when we work with the design and test system. And with this, let's say, way of working, you move away from the co-bonded or co-cured T-shaped stiffness. And we calculated that this version was slightly lighter than this version. So what we had to do is incorporation of optical fibers with fiber break rate sensors. Yeah, I think Martin will explain later on more how this works. During his test, it will be important to have these sensors available on these spots. So these spots were defined during the design phase of the program, and our goal was to incorporate the optical sensors. As already explained in my previous presentation, we did some changes on one of the 8 material guides to be able to feed through an optical fiber, and to see if it was feasible to position the optical fiber with fire placement. As you can see here, the feed rollers needed some modification. So if you have the metal version, which is good, obviously, for let's say the composite tapes, but not so good for an optical fiber. So we went to the soft rollers to have sufficient feed and pickup from the optical fiber. So when you start, obviously, you have to push the fiber through all these guides, and at a certain point it will be cut. And then, for the next start, you need to feed them. So the feed roller must be have sufficient friction between the fiber and the feed roller. And obviously, also in the creel unit, you should not have too much resistance, otherwise you will not have any feed at all. So a video how it was done, or to see it in real life. So here you see, let's say, guide 8 that we have reserved for the optical fiber. Here you see, just to make it, let's say, to see a visualization of it, that the fiber was positioned here in this location. So what we did is do several trials, because what we wanted to achieve is a full integration, full embedded fiber. So to fiber place a small gap, so this is a big gap what you see here, so we did several trials, but to fiber place a very small gap, and to be sure that we were able to position the fiber in between this small gap. So we did several trials with wider gap up to no gap at all, and then do the cure cycle and see how the fibers would be embedded. Here you see that a very small gap was used for, let's say, precise positioning. Finally, closing the laminate with additional plies, and this is then the final result. So if you look very carefully, we had about 8 optical fibers fiber placed this way. Okay, so okay. After the first couple of trials, we found out that what we call macro bending, some people call it also micro bending, but bending in the fiber will have an effect on signal loss. So if there is at a certain radius, you will lose strength of the light that goes through the fiber. So losing a little bit of, let's say, of light strength is not directly an issue for getting data, but at a certain point, if you have it several times, you will lose data. So what we try to investigate is to see what kind of bendings are critical, to have signal loss with optical fibers. So we did several trials from, let's say, a very small step up to bigger steps, just to see what happens. We knew already, if an optical fiber gets out of the material, that it is very sensitive to be broken. So you need some kind of a coat around, it's a tube around, that if it goes out of the product, that you have sufficient protection for the optical fiber. So you see here the optical fiber, and also that in between here you have the fiber break rate sensor. Gideon will explain a little bit more about it, but this optical fiber already has a coat around. So the real glass fiber is much smaller than you see over here, and the combined diameter is a 0.15 millimeters. At least it was the one that we have used. So it is our goal was also to have a ply thickness that is in line with the thickness of the optical fiber. And thinner fibers are available. So if you have thinner plies, even then it is possible to use optical fibers. So one of the challenges was obvious also to get the the fiber out of the material, that there is still room for trimming, and that for this compression panel that you have sufficient signal, so without signal loss, a bending of let's say the tube that includes the optical fiber, so that you can still use it after trimming. In the autoclave, as you see here, this is a tacky tape dam, you can see here. We also found out that if finally, of course, if you want to gain data during the cure cycle, you have to go out of your vacuum bag with 100% vacuum tightness, and for the rest you have to bypass or at least go through the wall of the autoclave. In the next slides, show you how we did it together with Photon first. But what we found out for the first trials, that if you want to put your fiber on top of the tacky tape, it gives you some issues. There are several ways to solve it, but one of the things was to 3D print a very simple guide to be sure that you don't have any bending in your fiber and you lose signal when the pressure on autoclave is increasing. So several trials and results, and after all these trials, we knew exactly what to do to end up with such a solution without any signal loss. So here you can see how the bypass, or let's say the through autoclave wall solution was given shape. So we had let's say a special flange, as you see here. Here it is more in detail, and it was pre-treated in a special way. This was all prepared by Photon first, and we just mounted it on one of the flanges of our autoclave. So that was the way to for the feed through to the autoclave wall. Finally, we have connectors here. You see it also from this here, and on the edge of the autoclave table. So from one side we have the fibers coming out of the product. On the other side, you see the connectors that go to the the through wall, the feed through the wall. So connectors will help us to click on the whole system and to click off again, and to go to keep it that way for the next product if you want. The same was obviously for the synthesized solution. So we had the very good working and nice curing sensors from Nikos. We have the durable sensor located here in this this plate. We have also the disposable sensors used, and also for Nikos system there was let's say a special flange designed by Synthesites, and up to high temperatures, up to 200 degrees we tested it, and up to 6 bars we did a safety test that all passes the test successfully. And last but not least, as already explained by Nikos, the very nice simulator that we have here. So also the equipment of Nikos was involved for this use case. So and that was pretty much having almost all partners involved for this use case. So here you see my colleague Ronald, and as you can see, he's very happy with Nikos system, because we bought Nikos system, and let's see what he wants to tell us as part of the virtual lab tour about the system from Synthesize. Just please let me start the video. Hopefully the audio will be okay.
We cannot hear anything, Wilco.
Not? Okay. I hear it here very clearly. I have a separate movie. So stop sharing for a second and then try to start the video separately. So do share and then the video. Optimize for video, what I learned from Nika.
My name is Ronald Klom.
Do you hear any audio now?
Yes, now it's working. Wilco,
okay, thank you.
Colleague of Wilco Gerrits. And just to show you today that we're doing a vacuum infusion with BMI resin using the IsoJet machine over there, tool and vacuum bag in the oven, and this equipment over here to monitor the resin resistance using the Shear simulator. And actually there's 2 resin arrival sensors in it as well, at the beginning, at the end of the laminate. We're just at the stage of warming up the resin for degassing, so we're monitoring the temperature and the resistance of the bit of resin in the Shear simulator with the temperature of the degassing as it is, which we now have to control using the fluid controller from the temperature on the IsoJet machine. As soon as we're starting infusion, we're going to take the temperature from the oven and log it in on this one, and from there on we'll track and monitor the resistance of the resin while we're doing the infusion, get a better control of this tricky resin while infusing. Now we've started with the real infusion. The temperature in the oven 126 through the thermocouple, and if you then look at the Shear simulator signal, the temperature and the actual resistance, this is the line or the value that we're going to keep track of. If it rises above a certain level, then we're going to heat up the oven again to push the viscosity and get the last bit of resin in. Yeah. My name is...
So perhaps it sounds a bit complicated, but it isn't. In general, with the simulator, what we have is just you know, a thermocouple that's inside the material, and the simulator here simulates exactly what happens into the oven at you know, the spot of the thermocouple, and then we can exactly see what happens with the resin system and act on that. So it's a very good, helpful tool for us to work with, let's say, complicated or let's say complex resin systems. Okay, now I go back to my presentation again. And then I think we have a new video. Yeah, so audio is not so important for this one. This is one of the videos where we also show the equipment of Apodius again. So this was during the M18 meeting just before COVID. So you don't see any masks here. It was just before that COVID became critical in Europe. So please let me show you this video. So here you see Rolf Evenblij from Photon First explaining something. Here you see Alexander from Apodius explaining his system. And I think this part of the video already have seen. So the equipment of Apodius was installed in our machine, and let's say the software of Apodius was connected to our database. Here you see you know, a combination of positioning the optical fiber together with the system of Apodius. And here you see also that Nikos explained how his system works also at NLR during the same session. So it was, to my point of view, quite a successful meeting that time. Yeah, so in terms of hot forming, this is a part of the video that is available on the internet. So if you want to see the rest, it is available. but the equipment that you see here behind was also used for hot forming of the preforms, the U shapes. There will be another video that shows you how it was done, but to give you an impression about you know how this equipment is situated, how we normally do it with pick and place. In this example, you see dry fire material that is being pick and placed. So we have you know, laser control to check about precision. Here it is pre-compacted, debulked with an infrared heater. So vacuum is positioned, or let's say is applied on the dry fibers. Then the compacted preform will be put on top of a shape on the other side of the infrared heater. And here we will apply vacuum again and also infrared heatings to find the let's say the pick and drape part of the whole process. So it will be draped on top of a certain molds and gets pretty accurate the shape. So how did we use this equipment for the U shapes from the ANOVA use case? That's what we see here in this video. So first of all, we have a mold available. There will be some foil on top, you know, to prevent that you will have tackiness between mold and your material. Let's start the video. So the fake blanket is being closed. At that point, only minor vacuum is applied because it is, you know, the material is not heated up and would give you some wrinkles. And if you have, let's say, thick preforms, then the infrared unit is moving over the preform. And as you already have seen in the previous part of the previous video, then heat will be applied by infrared heaters inside this this unit. So now infrared is being applied. The temperature underneath the preform is measured, and when it reaches the right temperature, vacuum is slightly applied stronger on this preform to shape it, as you can see here. Now it was cooled down, and during cooling down, it shortly heats up again to be sure that heat distribution during cooling down is done correctly. You can still see also the, you know, where we have the thermocouples to measure the temperature, and this is then you know, the final result after hot forming. And if you move it upside down, see it here at the inside. So if you do this several times, or maybe even several preforms in one cycle, it's quite a quick way of very accurate, you know, shaping this U shapes. So yeah, in general, as already explained, we start with fire placement of the skin. During fire placement, optical fibers with fire break sensors were integrated. Tubes were applied during this system to you know, to protect the optical fiber against possible damage to make it more robust. The the hot formed preforms can be combined together. In between, there will be you know, an extra laminate to reach the required thickness for the blade stiffener. Here you see the cold plates are being applied inside the vacuum package, and then it's a matter of completion of the vacuum bag and perform the cure cycle. Yeah, I skipped the cure cycle, but you can imagine that you know, you already saw the pictures with having the equipment from Photon first and the equipment from Synthesites available in front of the autoclave. So that's the step that you saw in one of the previous slides. So after that, it's you know, taking out, debagging everything, and then going for machining. And this was obviously, I think, the most interesting part to see, can we trim the panel without damaging the optical fibers, and that was done successfully. So here you see the final results from the panel that we have manufactured. So you still see optical fibers coming out of it. The tube was also embedded inside the material, and from this point on, you can bend the tube and without having any loss of signal. So it is a very simple way of getting access to the fiber, and but it's also a very effective way. Don't know if I still have time. Otherwise, maybe once again show you the video from Apodius. Just please let me start it. Really a pity that Apodius is not available anymore to to work further on their, to my point of view, very good working system. We work together with a lot of partners that do the same in this area, but Apodius was, to our point of view, a really good partner to work with. Their system is was very reliable, and also the connection with the database was very good. And yeah, it would be helpful to have this system on board also at NLR. Unfortunately, we finally we decided not to buy the system because support is also critical now. They are not there anymore, but it is a very beautiful system. And that is the end of my my presentation.
Yeah, thanks, Wilco, for also mentioning the database system. This hasn't been presented in the whole discussion yesterday or today, but if there's interest also, anyone in the line here, you can also approach us, since we do have developed quite a bit on this, how to structure data, how to access data from the different systems, no matter if it's a Q sensor or that optical measurement system, and then yeah, to make decisions based on this information. But now I think, Martin, you'd like to continue.
Yes, can you still hear me?
Yes, we can.
Okay, perfect. So, welcome back to DLR, and thanks, Wilco, for explaining how this wonderful test article has been manufactured. I'm standing here currently in our sample preparation area. We will initially go through how sensors are applied. After that, we will go over to the facility itself, discuss how boundary conditions, how the test sample is integrated into the facility, and have a look on that. And afterwards, we will conduct together a live testing to demonstrate to you how our procedure of combined thermomechanical testing is performed. The objective of our testing is to investigate, of course, the mechanical behavior of the structure with varying temperature fields, very local or very more global fields, any different kinds, but also to demonstrate the performance of the novel material solutions and the structural performance. And further, of course, to produce a certain database that can be used within validating of a numerical analysis. So for such validation purposes, we need, of course, a lot of sensors that have to be applied. We want to measure, of course, a global distribution of data, global distribution of temperatures, and also of strains and deformations. As you can imagine, we are having here quite a lot of sensors already installed. And I want now to explain you further details on how we are installing those sensors. We have here placed another camera that shows a more detailed view on the structure. Okay. So as you can see, for instance, within the skin field here, there are a couple of strain gauges installed. We have used at a few positions longitudinal strain gauges only, but also rosettes. Those strain gauges can resist temperatures of up to 350 degrees Celsius. And close to each strain gauge, there's always a thermocouple located. Those temperature information is required to correct the strain signal that we get back from the measurement. The strain is very sensitive to temperature. We have a deviation of the K factor itself. but we have also thermal output and a thermal mismatch between sensor and composite thermal expansion coefficient. And all those parts have to be integrated into a certain correction methodology to get to the correct strains back. So we have placed quite a lot of thermocouples also here, also on the string of foot and on the top, on the blades, to measure global temperature deformation. As you can see by those yellow spots, we have used polyamide adhesive to apply the sensors. This polyamide adhesive can resist temperatures of, also up to 350 degrees Celsius. It must be applied within a special curing process. Curing is performed here at 200 degrees Celsius with area surface pressures required. And after that, we require a certain post-curing step close to the surface temperature. As you can imagine, for applying all those different kinds of sensors, also here at the stringer blade, this is a very complex and long enduring process. Therefore, the integration of fiber bracks, which we have recently seen in the video, was a good option to study if the measured strains and temperatures are comparable to those strain gauge values. You can see here at the end that there are the tubes exiting the structure. They are going around here. Then we have a certain setup that was required to feed out the cable out of the oven for applying those physical sensors, because this peak tubing right over here is temperature resistant. All at the end right here that comes out of it is not anymore temperature resistance. And at the end, finally, we can plug those plugs into the interrogator for measuring our fiber brack sensors. So that's how we apply our sensors. After we have finished our sensor application, we require a certain further step before we can integrate our structure into the facility. So here's the first structure that we have already tested within the project. As you can see here on the stringer side, this is the side that gets heated. We are applying a black coating to ensure uniform emissivity. This ensures that heating is performed in an equal way over the whole surface. On the other side, which is the side lying on top, we are applying a black-white sparkle pattern, which is required for digital image correlation and measuring of deformation. As you can also see here at the left and right-hand side, this is the position where the structure is integrated into the facility. And I will now go over to the facility to explain you how it is integrated. So this is our Thermex facility that is capable of testing thermomechanical load conditions. You can see this structure, the test article is located right here in the center of it. We have a fixed clamp right over here and a movable clamp right over here. The test article is then, somewhere placed in between, like this. So the black-white sparkle pattern on top, where we measure with our digital image correlation system, the Aramis system of GOM, right over there. And we additionally have placed the thermography camera right over the structure. In the current version, we have a test article implemented that uses only 2 stringers. So it's a bit smaller compared to this, but never mind. So we can test structures a total of a maximum length of about 1 meter. I forgot this. Maximum length of about 1 meter and the maximum width of 80 centimeters. Structures can have different shapes up to a maximum cross-section thickness of 10 centimeters. So we can test those different structures, curved ones, but also honeycombs or other assemblies. To explain you about the function of the facility, I'm showing you a scheme right here at the top, at the front. So your left, which is quite right over there, should be the fixed clamp, which is placed here. At your right side, which is right here, there is the movable clamp, which is here. Behind the movable clamp, there is this blue box here. This is the motor of the facility, and the motor can apply forces which are acting in axial direction. Yes, as shown by the arrows. We can apply forces of about of up to 400 kilonewtons in compression direction, so this would be in this direction, or in tensile direction. In the current panel, we are investigating also in SuCoHS. We were investigating the stability behavior, so we are applying compression behavior. So this was all about the mechanical load introduction. Now let's talk about the thermal load introduction. On the lower side of the panel, you see the infrared heaters. They are located right here in the inside. The infrared heaters have a total power of about 2 times 85 kilowatts per kilowatts. We can reach temperatures of about 1000 degrees Celsius in maximum, quite a lot. And in between the infrared heaters and the test article, we can place specific apertures. I have positioned some of those apertures here at the front. As you can imagine, they are placed between heaters below and structure above. So the heaters are only radiating through this little hole, through this little spot, depending on the aperture geometry, and thus only heat a part of the structure, which produces our local temperature field. The apertures are positioned in such a little frame, depending on the test article, and how we place this frame on below the structure, we can see with this camera. I've put another camera here. This camera, the aperture is then hinged right over there below the structure. You can see the structure in black, the black coated sides. And on the left side you have, and on the right side, you have the clamps that are reinforcing the structure. And on the lateral edges, and on the other side, you see that there are insulation blankets. Those insulation blankets are required to distinguish the thermal boundary condition between the hot side here below the structure and the ambient side at the top of the structure. So let's have a look on how it looks like if the structure is radiated by the structures. So the infrared heaters begin to gloom. Now the full power output is applied to the structure. And then we just turn it off for a second so I can explain it further. You will see also how the structures are controlled later on. The electrical power of the infrared heaters is controlled by a specific sensor that is applied to the structure. In the current version, we are using a thermocouple that controls the heating unit to a specific temperature. And you will see later on that the infrared heaters are oscillating somehow to stay at the target temperatures. So I've additionally placed a camera here on top of the frame so we can have a deeper look on the structure itself. Here you see now the 2-stringer test article again. Again, on the lateral sides, you see the isolation planes now from the different sides. Again, preventing from hot air to flow around the corners and the side edges to ensure that we are having a uniform thermal boundary condition at this side. The test article is clamped, reinforced by 2 potting frames. The potting frames are filled with a concrete material. This concrete material is temperature resistant and has a quite low thermal expansion coefficient, close to the one of the material itself. By this, we are reinforcing the load introduction and ensure that the test article is not kinking at the load introduction where the compression force is applied. Those potting frames are special because they are segmented. You can guess the segmentation here by those, by those parts, metal parts. This segmentation allows that the structure can deform in transversal direction. At the backside of the potting frames, there are cylinder roller bearings that ensure such movement later on. At the structure itself, you can guess where the sensors, so the strain gauges and thermocouples are placed. In addition to those local sensors, we have applied additional sensors here by those rods, which are axial displacement sensors. Those axial displacement sensors here at the edge of the structure are measuring the out-of-plane deformation of the structure. We have put a few on top of the potting frames and also on the clamps to measure if a certain rotation is ongoing within the load introduction areas. On the side of the structure, you can always see such a laser triangulation system and another displacement sensor. Those sensors measure the actual displacement that is applied to the structure in order to compress it. They are later on used to evaluate our load shortening behavior and to evaluate the structural stiffness overall. We have placed at each side one of those sensor pairs to evaluate rotations in this direction within the sample plane. We are further investigating if the thermal conditions are having any effect on the optical output of the laser triangulation system. So as I have now explained about how the structure is integrated into the facility, we will now together conduct a further test. I will go into the preparation room again, which is also our control room, and we will have a view on a typical test procedure. So I've collected a few, I would say windows which are showing sensor signals. On the top left side, you can see all temperature thermocouple signals within the chart itself. The numeric quantities close to it represent thermocouples that are placed on the central skin of the structure. Below you have strain gauge sensors, similar thing. All sensors are located within the chart, and only these strain gauges located within the central skin field are shown as numeric quantities. In the lower left, you can see the force over axial shortening. So, which I recently said is representing the laser sensor displacement and applied over the force. So you will see when we apply mechanical force that a certain load shortening curve is shown there. At the top right, you see the two views within the facility. In the center right, you can see a thermography image. You will later notice how this optical system is used. And on the lower right, you can see the RMS system showing the distortions, out-of-plane distortions. There will be quite a bit of lag. Now I'm talking about how we apply the forces and temperatures. Initially, we start at room temperatures, which are currently present. We are then heating the structure up to our position 1. 1 is where we reach our target temperature. This will be 150 degrees Celsius within the current test. After that, we are heating the structure through to reach a certain stationary state. In position 2, there will be a certain horizontal a quantity of strain gauge signals. In position 2, we have applied a certain preload, which is due to the thermal expansion and our preload. We remove this preload, mechanical pre-force, to a value of 0.5 kilonewtons in position 3. And from position 3, we are then applying our mechanical force up to position 4, the maximum force we want to apply, which is currently 35 kilonewtons within our present campaign. After that, the main test is finished. We remove our forces and we remove our temperature afterwards. So let's have a start on it. Let's heat the structure up. Okay. So as you can see in the thermography image, the heaters and also the sensors are certainly acting as heat sink. And this within the tests this different temperature gradient will reduce within the test as the structure heats through. You can see that we have reached our target temperature of 150 degrees Celsius, and we have overshooted the temperature within a single thermocouple 8. This overshoot is here placed in the thermography image at roughly the center left side. This is due to the alignment of the structure and due to the nonlinear power output of the heaters, infrared heaters in axial direction. You can see within the strain gauge signal that we have almost horizontal behavior of strains. Some are still heating, which are placed on the stringers. So let's continue with reducing our force. We are now reducing the force. You can see also in the load shortening curve that our preload is reduced until roughly 0.5 kilonewtons. You can also see in the Aramis signal on the right-hand side that there's certainly something changing. In the meantime, there's also a slight change of strains. We can now increase again our force to 35 kilonewtons, and you will see now in the Aramis, in the out-of-plane deformations, that the structure deforms quite a bit more. In the meantime, the strain gauges, two strain gauges are deforming in tensile direction. The others stay all in the compressive, so in the negative quantities. The thermocouples, especially the ones placed in the center at the top, you see them show almost constant behavior, I would say. Some thermocouples that are placed close to the potting behave still elevating the temperature. So in the out-of-plane deformation, you see that we are now changing, especially at the outer skin field, from 1 buckle to a 3 buckle phase. We are approaching our maximum force of 35 kilonewtons. So this is our final shape within the present test campaign. It is not the buckling pattern as we were intending it, but here certainly the small scale structure, which has 3 edges and only 1 single temperature field, is interacting. After we had recently just holded the structure for the force for a few seconds, we are now reducing our force and turn off the infrared heaters again. And you can turn on the video again. And so it's live. Yes, thanks. I was just scratching the first test article. The tests we have just carried out are conducted for different temperature conditions, not only the global introduction that we have seen yet, we are also applying it for the local ones, as you have seen the apertures. We are repeating all those tests for different target temperatures, starting from room temperature and going up to our final temperatures, which is for the cyanide ester material 250 degrees and possibly more than that. Between each temperature test, we are conducting reference tests at room temperature to investigate if there are any damages within the structure, if there is any aging or any other deviation. By this, we produce a lot of data that serves for investigating the mechanical behavior at such varying thermal conditions. We are also demonstrating the maximum capabilities of the structure and when it begins to degrade. And we are, of course, feeding for our validation of our finite element analysis. So that's the end of my presentation and my lab tour. So if you're interested into the topic, you can see at the right-hand side my personal information. If you're interested, just give me a call, write me a mail. You can also find our institute within the QR code right over there. And at the end, I want to thank all the partners within SuCoHS, of course, for this very interesting project, for the nice collaboration, and also thank the EC for funding the project. Thanks. If you have questions, feel free to ask.
Yes, Wilco and Martin, the both of you, thanks a lot for your preparation. This is not so easy to prepare things like this. And now it's we only have 4 minutes left, and before we are starting the classical conferences, there is a question in the chat. And Wilco, maybe this is something where you could get in contact directly with Alberto Fernandez, if possible. So that could make it easier for you to discuss the aim of the question and to get in greater contact. If there are further questions, please also don't hesitate to still put it into the chat room. And I think we will have also the option to answer those questions, if not answered yet, in the next tour, which is planned for the afternoon, if it's fine for you. So then it gives us the chance to start with the classical presentations on time.
Yeah, exactly. So we're having a second tour. We can also adapt a bit if questions arise, probably. So thanks again.
Thank you.
Keep the facilities prepared. Don't cool down.
Yeah.
So now we have still 2 minutes. Maybe the one or the other would like to have a 2-minute break again before coming back to the desk. And then meanwhile, we can prepare handing over to the presentations, which will be shared by Markus Grob from FHNW. But give us 2 minutes until then. Meanwhile, the question, Rafik, are you also on the line already?
Yes, I'm here. Hello, Tobias. How are you doing?
Yeah, good.
Well.
Nice to see that it works. So you got your presentation and you're showing it from your PC, right?
Yes.
Good.
I will send it to you later.
Yeah, you can do that afterwards, of course.
Sure. Nikos is here?
Nikos is also here.
He should be.
Yes, he is still.
I'm here.
Okay. Hi, Nikos.
Perfect.
Okay, there are just a few seconds left. Since all the presentations do not have so much time itself, only 15 minutes, I'd just like to start to introduce Markus Grob, who will be moderating the next session. So Markus, thanks a lot for accepting and willing to do that. Before you've been in industrial companies for a few years, and you have joined Fachschule Nordwestschweiz, Northwest Swiss college, and then you are now the head of the Institute of Polymer Engineering, and that also giving lectures in chemistry and analytics, and also the group leader for chemistry and analytics, what I took from your CV. So thanks a lot again for taking the share, and so please, I think you can take over from here.
Thanks a lot, Tobias. It's an honor for me to present you the part on the end-to-end analysis, and I would like immediately to hand over to Rafik Hajiria. And Rafik, if you can give us in the beginning a few details on your life, that would be great. And then let's start. You have 15 minutes.
Thanks, Marcus. Hello all. Thanks, Tobias and Nikos, for inviting me to share with you this talk. So my name is Rafik Hajiria. I'm research engineering at Safran Research Technology, mainly dealing with structural health monitoring, let's say from sensing techno algorithms and system integration. So let's say, I am part of Safran since 2016, but during the past, I have done my PhD in structural health monitoring at Arts et Métiers in France, then have applied a postdoc on electromechanical stress reversal for Safran Nassel and things like that. So my background is mainly about sensing techno algorithms to try to enable, let's say, predictive maintenance and condition-based maintenance, we'll say. But they focus mainly on structural part, mainly mechanics, composite structure, also metallic, dealing with trying to health assessment about lamination and corrosion and things like that. So this briefly, let's say, introduction about myself. Let's say that for this presentation, I would like to share with you, let's say, regarding morpho dissemination context. So, and thanks again for inviting me to this workshop, we will say. So let me just now go into the deep of the presentation. So as you know, so the global MRO will grow in the future. So here you see presented just quick information about the global MRO demand. So before the COVID, however, we expect also that this, even if the expectation will be shifted within the years, but we expect also that this the global MRO demand will also grow. Regarding this part, so the engines is mainly a great part regarding the MRO. And we would like, let's say, to, as we will have a lot of, let's say, airplane and things like that. So we would like to enhance the strategy regarding the future of MRO. So let's say, as Safran we are OEM and we manufacture and design nacelle, landing gear, engines, and things like that. So our idea is that we would like to enhance our, let's say, knowledge and also expectation about the MRO market, and also to enhance lifecycle management of our product. So this is why we are mainly interested about structural health monitoring. And for sure, the idea is also to accelerate the integration of new sensing techno in our project, so that to prepare the future. So morpho, so this is why the SHM concept, as you know, so the idea is that we have an onboard sensor to try to acquire data and get information about the health assessment of our structures. But for sure, so in this sensing techno, there is a part which will be integrated within the aircraft or within the vehicle. However, electronics will be off board, and the data acquisition and the analysis will be off board. So SHM is a techno. However, the challenge is that we have a part which is mainly on board, and also a sub part which can be also an off board. And these are naturalists, I would say, from the SAE International, which I belong, so I work also with industrial partners within an IRP 6461, which has been published in August 2021 about the interest of structural health monitoring for regulation and standards. And let's say, allow me to share with you just some achievement from Delta Ireland, the Delta Tech operation, where we see that there is an interest of the MRO regarding the integration of structural health monitoring system within the inspection. Here you see that there is a program between Boeing and Delta Tech operation about the integration of sensing techno for, let's say, an NDI inspections, because the idea of Delta Tech is that they see this techno as an NDI, integrated NDI inspection. And here we see that there is some sensing techno which has been integrated within the aircraft. And we see that a guy from the maintenance, which, let's say, take an acquisition system to interrogate the sensor and get information about the health assessment. For sure, this is not, let's say, this only about the proof of concept, we say. It's not used, let's say, by the operator, but we can consider that when a company like Delta Tech Operation take this opportunity to test such techno, we see that there is an interest to use it as a new inspection tool, so we'd say. So and also there is the FAA and the authorities has an interest about structural health monitoring. So this is why I will say that they have drafted which we call an advisory circular 48218, and this one has been also addressed to the MSG3 the consortium to talk about the opportunity to have a health monitoring system to try to respond to the maintenance strategy. And also a new issue paper has been also drafted and presented to the MSG3 consortium to talk about the interest of having a health monitoring system to move forward, I will say, the traditional inspections that we have, and also to move forward condition-based maintenance. However, as the aeronautics is mainly conservative, it's a great challenge, I will say. But when we see that the authority has an interest about this techno, we are convinced that that we can use it in the future. I'm not talking about the actual program, but we are talking about program that will be launched maybe in 2030 or 2035, but we are preparing the future again. So this is why I will say that from Safran perspective, we are participating, I will say, to Morpho projects. So this one is funded by the Europe. And the idea of Morpho is that we would like to integrate sensing technology to get health assessment of our composite parts, Mainly the interest is about an engine part, which we call it the fan blade. And the idea is that we are in a circular economy, where for sure the interest is that to think about a new design and trying to move forward the damage tolerance instead of the safe life design. And for sure about the performance, we would like to enhance the operation of our equipment and things like that. But what the challenge, I would say, that our idea is that when we talk about integration of the sensing techno, we believe that the sensing techno has to be taken and tackled during the life cycle management of process of an equipment, mainly from the manufacturing process to the operation, also to the recycling. So this is why in Morpho partners, so we are about 9 partners. We have Sentisite, represented by Nikos. We have a sensing provider like FiSense, and also many companies based in the Europe for sure. And this project is managed by l'École nationale des arts et métiers in Paris. And we, let's say, and Safran Research Technology is a part of this. And we have also an advisory board composed by the EASA, Stanford, and other researchers from the Europe also. And if I continue about Morpho, so the idea is that to enhance the life cycle monitoring of 3D woven composite part. From the manufacturing process, we are using the RTM process. And our objective is to integrate the new sensing technology within the RTM process to get to enhance our knowledge on it, and also to analyze the data and try then to control this process so that we will have a repeatability between our manufactured part. And during operation, we are talking for sure about circular health monitoring in the sense of health assessment and usage monitoring. Regarding the health assessment, we have an interest about diagnostic, also prognostics, and remain useful life. And we have an interest about impact events and stuff like that. So the idea is that to get knowledge about the detection of an impact based on this different sensing techno and move forward, let's say, the remain useful life. And at the end, so we would like to recycle our let's say 3D woven composite to try to embed it within the circular economy, where the idea is that this recycling process will be used to manufacture new projects and things like that. So our proof of concept within this Morpho project, we are using what we call the foreign object damage panel. Such a panel is mainly used in the RMT to test structures regarding, let's say, impact event. And this foreign object damage panel is a substructure of fan plate. And the idea is that we have to practice and develop techno within this proof of concept. So many sensing techno will be integrated within this within this FOD panel that we are undergoing manufacturing, and we will demonstrate the ability to develop, let's say, a sensing techno for the process monitoring and also for the SHM related to the operation. And here, just a brief presentation about the RTM process. We have many stages. And the idea is that we'll integrate sensing techno for the RTM process to monitor the temperature, the curing process, and things, and many, let's say, physical parameters that we would like to get knowledge on them. And then in the future, we would like to control this parameter that have to get a repeatability between the manufactured part. And once this, let's say, sensing a part of the sensing integration, sensing techno are okay, we would like to use the sensing techno as a part of the SHM operation part. And here it's just we are undergoing manufacturing an FOD, let's say an RTM mold, which is compliant to our design. And the idea is that to integrate sensing techno from synthesite and other and fiber optics and things like that, so to get knowledge about this RTM process. And when okay, so we would like to use this sensor for the SHM operation. And regarding this part, let's say our SHM is concept and techno, and it is composed of many techno element. We would develop also electronics that will help us for sure to acquire data and transmit the data. And also there is a great part within this project related to data analysis, based on advanced signal processing and also artificial intelligence to move forward, let's say, the condition-based maintenance. And we have mainly an interest about, let's say, the remaining useful life of our proof of concept before reaching the critical damage state. So this is mainly the concern of Morpho projects. So that's enough for me. Thank you.
Thank you very much, Rafik. Very nice presentation and absolutely fantastic in time. So I will directly, we will handle all the questions at the end, and we will go directly to Gideon Langdijk. And are you in? Yes, I see you. Thank you. Gideon studied applied physics in Delft. Then he spent 4 years in Shell Wells R&D, working mainly on topics direction tribology and integrity, well integrity and high pressure testing. Then he made a little short work at TNO, and now since last year he found his job at Photon First. He's working there on industrial applications on novel integration, photonic sensing solutions. He focused there on energy and infrastructure. And we are happy to have you here. And we have already seen some of the photon first things which we have used in SuCoHS, and you will give us certainly now more details and also what are the potentials of the system. Thank you very much. Gideon, the stage is yours.
All right, Marcus, thanks. I hope, can you hear me correctly?
Absolutely. We don't see your presentation yet, but...
Just give me one moment. Can you see it now?
Not yet. Yeah, it's popping up. Great. Not yet in the presentation mode, but yeah, fantastic.
All right,
Go
thanks
ahead.
a lot.
Thank you.
Yes. Okay, so today I want to share a little bit more about our Photon First's main contributions to the SuCoHS project. Been mainly on 3 parts. And at the start, I would also like to share a little bit about integrated photonics. We've been working on the goals of the SuCoHS project, mainly looking at composite life cycle monitoring, so the curing process and the production, and also structural health monitoring applications after production. We have worked together with Onera to see if there is also applications in fire detection. And we've done a lot of work together with NLR. And at the end of this presentation, Frank Groteman from NLR will take over and tell a little bit about the work they have done on impact detection using these systems. I have to apologize for my cat. He's a little bit grumpy today. You might break in sometimes for a little bit. So our systems are based on photonic integrated circuits. The main reason why we choose this is that we think that these systems become a lot more scalable, and also this allows us to make smaller systems for fiber Bragg rating measurements, and not without impacting the quality of our measurements. Our systems can measure pressure, temperature, strain, also the shape or acceleration. It works through sending light through optical fibers. The fiber Bragg ratings cause reflections that we measure in a spectrometer. And the center wavelength of these reflections tells something about the deformation of this grating. So in a sense, you are measuring everything at once. And by doing proper sensor design, you can define really what you are measuring or what you want to measure, basically. And you can measure multiple measurements in one fiber if you want to. We have several commercial systems available right now. Also, several of our modules and systems have been successfully tested and validated for aerospace compliance and have been determined airworthy. Yeah, that's. If you want to learn more about our systems, please feel free to contact me. Yeah, so our sensors have been used in a lot of applications. There's a couple of examples, and already the stuff that we have been doing in this project. On the left, you can see how large the fiber actually is, 0.1 millimeter for an uncoated fiber. Some applications at the bottom for shape sensing. So the composite life cycle monitoring, a lot of this work has been done together with NLR, and we've already seen a lot today and yesterday about this. From our part, what we dedicated to do was design a sensor system and an interrogator system to monitor the composite panels during the curing cycles. So that gives them some requirements on temperature and pressure, also on tensile strength. And also, we have used the automated fiber placement technology to embed the fibers. We've also done manual placement of the fibers. So, so the sensors that we used have, well, there's a couple of decisions that you can make. Of course, micro bending can cause optical losses during your measurements and also during the curing cycles. So you can select specific optical fibers that are less sensitive to this. We decided very quickly on to use a primary coating to increase the tensile strength. So these coatings typically reduce the temperature rating of your fiber. For this application, we decided to go with a polyamide coating. The main advantages of this are the temperature resistance, which is in spec, but also the thickness, which is almost negligible. It will less than double the fiber thickness, and also the tensile strength is increased a lot with this coating. So at NLR we created a panel for the Aeronova use case. You can see on the left here the design that we made for the placement of the FBGs, the bottom layer. So for this use case, we had to overcome a couple of obstacles. So as I mentioned, the tensile strength of this fiber is actually quite high, but the main issue is with bending points within the panel and also the setup in the autoclave. So you have a specific pinch point at the place where the fiber leaves the composite, but also a pinch point at the location where the fiber leaves the vacuum bag. And then there is a couple of, well, moving parts, of course. And and also we had to get the optical signal outside of the autoclave because we didn't want to put our interrogator in there in the end. So the sensing part and the part that's fully integrated in the composite is only coated with the primary coating of polyamide. And then at the first interface, which you can see on the far right here, we have a secondary coating with Teflon material, and then there is also a nylon jacket that we used, that we partially integrated within the composite interface as well. So this has two main reasons for this design. So it's of course a strain relief because the fiber is free to move inside of the jacket, and also it protects mechanically from the pinch point. And Wilco already showed a little bit of the 3D printed inserts we used for the vacuum bag, the leaving point. And now we also did the automated sensor integration together with NLR. The application here was similar, the way that this was inserted. So yeah. And we've already seen the video about how this was done. So let me continue quickly. So yeah, so the measurement design of these FBGs. So as I've shown before, if you do nothing, the fiber Bragg ratings will measure basically temperature, strain, and pressure at the same time. However, we decided not to alter or to decouple these measurements from these sensors. The reason is that there is a lot of different measurements within the autoclave, also unrelated to the FPGs. We can see the pressure and the temperature in the oven. So for this research, we decided to have several reference sensors as well as the FPGs that are inside the panel, so that we can later relate the signal that we've seen as a result of the pressure and the temperature increase, and that we can decouple them from the really interesting data that we want, which is the deformation of the panel due to strain during the curing and shrinkage. Example of that. So this is how the measurement looks from the different FBGs. We have the temperature plotted inside here as well. And basically, specifically on the right, we have a graph where we've seen the different FBGs in the part of the curing where where a lot of the setting is happening, and we can see the different relations. And then using the reference measurements, we can really make something about the different stresses and the shrinkage that goes on different positions. In view of time, let me quickly continue. So after curing, of course, these sensors still work and they can be used for structural health monitoring. Well, I think we have just seen also a lot of really interesting applications for structural health monitoring. And we think that these sensors are also very suitable for doing these types of measurements. And finally, we have the application of fire detection. So together with Onera, we have designed different types of sensors for high temperature application. In this use case, we decided to decouple the FPGs from strain. So we've done a primary coating with gold on these fibers, and then afterwards we also placed a steel tubing as well as a ceramic tubing around the FPGs to decouple them from strain. We then retrofitted these at Onera's fire test facility onto one of the composite plates for the Aeronova use case, which was done to check the fire resistance of this panel. So the fire detection in this test setup is done with an overhead infrared camera, and we wanted to look at if we can mimic the measurements with this camera with our fiber measurements, even at high temperatures. So I will show on the next slide I have the results, but these sensors operated up to 400 degrees in the test, and they were still working afterwards. We can see it. In the middle we have the correlate, or we have both the fiber measurement and the infrared camera measurement. Yes, and below we have a short animation of the fire test. So after this test, the fibers were still working, and we managed to disassemble them and take them back again. Now we found that calibration is very important with both of the applications that were shown. And we have done calibrations for temperature measurements before integration and also after integration, and that leads to the best results. And concluding that, so we have developed some techniques to embed optical sensors in composite panels. They are active during production and curing of the panel. We have generated quite some interesting data. And and afterwards, these sensors can also be used for structural health monitoring and also fire detection applications. I would now like to hand over to Frank to share something about the impact localization. Frank, are you here?
Yes, I'm here. Good afternoon, everybody. So my name is Frank Groteman. I'm going to present you a couple of slides on impact localization with optical sensors. And this work was performed at the Netherlands Aerospace Center, NLR, together with my colleague Jan-Willem Wiegman. Can you go to the next slide, please? And the objective here is to determine an impact event and localize the impact by means of optical sensors. And the algorithm we already had was further developed within SuCoHS to cope with strongly curved structures, and was demonstrated on a nacelle demonstrator from Spirit Aero, developed within SuCoHS, which you see on the upper right-hand side. On this panel, 8 fiber break ratings were installed, which was 1 optical fiber. And you see that in the lower right corner, a detail of it. And next to 6 of those FEGs, also a new type of optical sensor was installed, which is a rather bulky sensor, but this allowed us to measure at 1 megahertz, while the fiber break rating system was limited to 20 kilohertz, and I'll show you the difference on the next slide. On the nacelle, 20 impacts were performed, 20 locations, different locations, with low energy, 2 to 3 joules, which is very low. And on 6 locations, you see it marked by the white stickers, a higher energy impact was performed, ranging from 5 to 25 joules. And for that, a mobile impactor, which you see on the left-hand side, was applied. Now, the next 2 slides, I show you some results. So the objective here is, please continue to the next slide. Yes. So the objective here is we measure during an impact event the time response, in this case for fiber break ratings, the strain response during an impact event. By this, you can determine whether an impact took place. And more importantly, we can derive the impact location. Now, in the green dot in all 3 figures represents the true impact location. And the blue dots is the derived impact location. Now you see a difference, the error, and this is mainly caused by the fact that the sample rates is too low, because waves typically travel of the order of 1,000 meters per second in structures. And to have a more accurate result, you need higher sample rates, and that you can see on the next slide, where we applied the new optical sensor type with which we could measure at 1 megahertz instead of 20 kilohertz. And there you see that the derived impact location from, in this case, it is not a strain time response, but a different time response, it's a different type of optical sensor. You see that the impact location and the derived impact location more or less coincides. And that's my final word. The objective is here to determine, okay, there was an impact event. And if you have to send out an inspector, only a small region of the structure typically needs to be inspected. Okay, now the time is up. So
thank you
from my side.
Thank you to both of you. And Gideon, your cat made it didn't disturb you too much, and you made both a great job. Thank you very much. There are already some questions then in the chat, but I now want to hand over to Martin Liebisch from the German Aerospace Center. And you have seen him already in the virtual tour. Martin is research engineer at the German Aerospace Center since 2014. His expertise on thermomechanical analysis of composite materials and fire analysis is mainly on material characterization, numerical analysis, and experimental structural analysis, what he all brought into the SuCoHS project. Martin, please start.
Thank you. You should already see my screen.
We can hear you, we see your screen. Thank you.
Perfect. So my presentation now is more on the numerical topic which we have already seen. We have already seen the experimental way. This is about an enhanced thermomechanical analysis that is capable of exploiting existing structural reserves. I want to start with a short motivation. So this arrow here on the right is based on the publication of Hachenberg. He intentionally made this for impact damages, but I adapted it a bit to show the main conservatisms that are applied within a static thermomechanical load case. So we have at the bottom, we have our typical load definition. So limit load once in a lifetime multiplied by a safety factor of 1.5 leads to the ultimate load, which is the maximum load that must be withstand. At the top, we see the material allowables. So the worst case failure and worst case environmental conditions and a certain A or B value, depending on the design, must be withstandable by that loads. So in between now there is a certain knockdown factor, and because I've shown the mechanical load here on the arrow, this factor must be a certain function of temperature somehow. So in current analysis, the temperature is used as a discrete formulation, and I've tried to summarize how the maximum service temperature is defined from that. So we have a certain, in the left chart, we are showing the normalized strength values, in the right chart, the normalized stiffness components. The maximum service temperature is now defined by a TG, for instance, as again, worst case scenarios, subtracted by the so-called knockdown factor. And by this we reach the maximum service temperature, and this is the maximum temperature that shall be seen within service life. So again, also a worst case scenario, and the design must be adapted in order to fulfill this maximum temperature requirement. So now our idea is to reduce this conservative in a manner. So let's go further and think about what this means. So the left picture shows how the current approach is done. We take in our sizing approach, we take the worst case scenario, in this case a uniform temperature distribution, since we have a discrete temperature formulation, and set it equal to the worst case scenario, the maximum temperature. In a more realistic procedure, for instance, for an engine part, for the APU part that we've seen in SuCoHS, we will have a certain temperature shape, a distributed shape, where a maximum temperature is only seen in a really narrow spot. So this means that there are probably some load redistribution effects. And as shown in the right-hand side, showing stiffnesses again, the maximum temperature is only located in a really narrow spot at the center, and the surrounding structure have lower temperatures and thus also higher stiffnesses. So there are probably load redistribution effects, and our approach is here to apply a more realistic temperature distribution within the sizing or within the analysis approach. And this requires, of course, also a certain temperature-dependent property formulation. Now, there are, of course, different sensitivities to such distributed temperatures. For instance, in reality, I can imagine that the temperature field, temperature map that we are having in our structure is quite an uncertainty. We never know how exact the temperature map is reached. If the local heat impingement is more circular, or if in some cases it is more shaped like an ellipsoid, more wider, more narrow. This is a certain uncertainty how it is realistically impinging the structure. And then, of course, compared to the current approach here on the right top, a certain spatial temperature distribution and resulting temperature gradients will lead to a certain deformation of the structure. And this, of course, is sensitive for stability and also for strength failure. So how are those sensitivities interacting with the structural behavior? To consider all those sensitivities, we are using a probabilistic sizing approach for thermomechanical conditions. Initially, we selected, I didn't mention the thermal load equation that we are using to apply all those temperature conditions. So we are applying this equation in order to consider different temperature distributions. And there are different parameters in this equation that we can vary to reach the temperature distributions. And we initially select some of those in a DOE sampling design. On the right side, you see that there are a couple of analyses that will be performed at those discrete points. We conduct a finite element analysis at each of those points, and we'll get here, shown by the right circuits, we'll get some analysis results, for instance, for the buckling load or for the strength failure at those DOE points. By those points, we have our training points that can be used to train a surrogate model. this surrogate model then represents certainly a function of the design criterion for all temperature conditions, which are represented by the parameters. And based on this function that we now have, we can conduct an efficient probabilistic assessment and evaluate robustnesses and reliabilities, and basically also produce such PDFs as shown here on the lower right-hand side. So how are those deterministic analysis procedures providing the training points performed? We always produce individual stationary state distributions. So similar to the testing we've seen, a stationary temperature field, depending on the thermal load variations. As I mentioned, we are applying temperature-dependent material properties, and we are evaluating first ply failure and buckling loads. So initially, we get our thermal load field as input from the DOE. We apply it to our structure, and also other thermal boundary conditions will lead then to a certain temperature distribution determined within the heat transfer analysis.
Moin, grüß Sie, vielen Dank für den Rückruf. Ich wollte nur fragen, ob Sie schon meinen E-Mail bekommen haben.
Mute the colleague?
Perfekt.
Thanks. Based on the temperature field, we are then calculating, analyzing how the structure distorts due to a certain mechanical clamping. So the structure is now certainly also distorted, and this distortion then, of course, interacts with the mechanical performance of the structure when we apply axial loading, in this case again axial compressive loading, that leads to a certain buckling behavior. So those are our three numerical analysis steps, and after the analysis we can evaluate the results and evaluate our sizing criteria, like for instance here, local buckling and strength failure. Repeating this procedure for all our design points that we have seen within the DOE, we will have a certain set of results, as shown here for the load shortening curves in gray, and for the orange fields, the first ply failure variation, or in blue, the local buckling variations. Those results are produced due to 100 analysis. Based on this, we can then perform our probabilistic analysis. We can apply a certain load distribution to our input parameters, and we'll get then a PDF, a probability density function for our design criterion as shown here. Now, based on this, we can evaluate a certain allowable again, so very close to the material procedure. This allowable will now be a representative for the structural behavior, and we can see here obviously that there is a mechanical potential compared to the typical behavior that we would have if we consider the uniform temperature distribution at maximum temperature domain. And this is well explainable in this case, because at this 99% stage, or at any other position within the PDF, we will have a lower temperature because the maximum temperature is only located at a very small part of the structure. The effective temperature is lower, and within this little small region, there's of course is an effective stiffness change. So the overall structural stiffness is higher compared to this red line. Now, with this mechanical potential, we can save weight, for instance, by reducing a layer or reduce the stiffness. But there's another potential, what can be achieved in terms of temperature potential. Now, this is, of course, another question. If we can locally, if we are allowed locally to elevate the local temperature above the Tmax requirement, which is still a requirement actually, but if we are able to elevate it locally above that value, we could size our structure by shifting the effective temperature towards the red line here, and get a lower allowable of our structural behavior close to the intentionally buckling value. That's the second potential. So coming to an end, the the surrogate that we are producing has another exploitation method, which we have just seen. So the surrogate also enables to compare or to feed a digital twin and also to compare to our experimental results. So we can reproduce our experimental setup, reproduce our experimental conditions, and by this try to validate our analysis. So that's so far from me. Thanks for your attention, and if there are questions, you have my contact details. Thanks to the consortium again.
Thank you, Martin, for this presentation, and I'm sure there will be some questions which we will handle afterwards in the discussion time, and also for keeping the time. And I will directly go to the next presentation, which is the presentation of ARNOVA. And for ARNOVA, we have Juan Penche. I'm sorry if this is not pronounced correctly, but he's a stress engineer in the ARNOVA stress department. He's more than 10 years of experience in structural analysis, and especially in analysis with the FEM method. And he will give us introduction on how this methodology will be used in the SuCoHS project. Are you in, Juan?
Hello, Marcus. Hello, everyone. Can you hear me?
Excellent.
Okay.
We can hear you and we can see your presentation.
Okay, perfect.
Thank you.
Thank you. Thank you for the introduction, Marcus. Well, as you say, today I'm going to summarize the simplified semi-empirical method that Inigo introduced yesterday, and our team has been developing to support the fire certification test. Okay. I think it's okay. So as Inigo presented yesterday in the fire test certification test that we've performed with the ARNOVA use case, we applied both a flame and a mechanical load, but depending on the structure that we are testing, maybe the mechanical load is not necessary to be applied. So for this reason, we have divided our methodology in two main simulations. First, we perform a heat transfer analysis in order to calculate the temperatures and the degradation of the composite during the test. And then with these temperatures and degradation as an input, we perform a mechanical analysis to evaluate the residual strength of the degraded structure. All these simulations are performed based on the finite element method, and we have chosen as the software to be used Abacus, mainly because it's a powerful tool and has capabilities to define our own material model and internal heat fluxes by means of subroutines. Okay. Starting with the heat transfer simulation, the material model that we've used to define the thermal properties of the composite is a multi-phase model. That means that the composite thermal properties are calculated or are derived from the subcomponents' thermal properties. These are the fiber, matrix, and the hot gases produced during the decomposition. In addition, the composite thermal properties are also dependent on the decomposition degree of the composite. Together with this material model, we made some assumptions, such as we assume the volume of the coupon constant during the simulation. We also assume that only the matrix decomposes, and it does under inert atmosphere. That's an important point. And also that the hot gases produced during the decomposition of the matrix are considered as hot air in terms of temperature-dependent properties. Finally, the fiber thermal properties are considered as constant for the whole analysis. Well, to calculate the degradation of the composite, we developed a Python tool that optimized the parameters of the Arrhenius equation in order to fit the curve with the test results, the mass loss curve extracted from test results, and that was provided by Onera. Then, with this degradation, once we have this degradation calculated and we have the properties of each of the components, we can calculate the thermal properties of the whole composite. Here we have the equation used for density, specific heat, and conductivity. And here on the right, we have the evolution of these properties during the simulation. It's important to remark that all of these calculations, the degradation calculation and the properties calculation, is implemented in Abacus via user-defined field subroutine. Together with the degradation, we also have account for the energy related to this degradation. For example, we have considered the pyrolysis reaction energy extracted from TGA and provided by Onera in such a way that we provide incrementally as the degradation goes on in the coupon, in the panel. Furthermore, we also consider the heat taken by the gases that are exhausted, and these gases are the ones produced with the degradation. Note that this heat is negligible compared to the heat of the composition. Okay, as for the heat source simulation, our team has developed a procedure based on Newton's law of cooling to simulate the flame. This procedure has several steps. The first of them is consisting performing a fire test on a titanium plate. From this test, we recover the temperatures from the thermocouples, and in MATLAB we prepare some temperature maps that will be applied to a simulation of this fire test. Then from this simulation, we extract the heat fluxes, and with the Newton law of cooling, we extract an equivalent convective heat transfer coefficient that will be the input for the last heat transfer analysis of the composite panel. Here you can see the maps, the convective heat transfer coefficient map that will be applied to the composite panel. Also, we are applying radiation and convection boundary conditions on the back surface of the panel. Well, here we can see the finite element model that we've created for this simulation, both both of the simulations, the heat transfer simulation and the mechanical simulation. We are using the same model. Note that we have used one solid element per ply, and we've done this for accounting to account for the degradation of each of the layers independently. So we can have one degraded layer and the other not, and also to account for the heat transfer among all the layers. Here, this detail corresponds to A, B, or C stiffener, and this to D and E. Once we run this model, we notice that in general the simulation provides higher temperatures than the measures from the thermocouples of the test. But on the other hand, the simulation captures very well the shape or the map, the temperatures map of the test. For example, here we can see that the temperature map. These are the results from the simulation. We can see here that the temperature map is not symmetric, as it wasn't the flame during the test. So that's a good point. And additionally, the simulation also captured very well the area of the higher temperatures. For example, here these thermocouples, the 14 and 27, gave during the test the higher temperatures, and so do the nodes located at that point during the simulation. Here on the left, we can see a comparison between the measures of the thermocouples, which are the dashed lines, and the results of the simulation, which are the straight lines. If you pay attention to these two green curves, this is the thermocouple 14 and this is the 27, you can see that the maximum temperature difference is less than 100 degrees, 100 degrees, sorry. So we are quite happy with these results. Likewise, we extracted the map of degradation from the simulation. We can see here that the simulation correlates quite well the area degraded during the test, but also predicts that the strings will be mostly degraded. Well, in fact, during the test, they were mostly degraded. Here we have a photo from the picture taken after the test. And the same is happening in the skin. We see here is completely degraded, the upside, and the lower side is mostly degraded. And here we have a detail where some delaminations appear in the back surface. So it's quite close to the reality. Well, in this slide, I'm going to show you, okay, yes, this one. Some videos. This one will show the temperature, the variation of the temperature during the 15 minutes of the test. And this one we are going to show the variation of the decomposition degree. So it's quite fast. So I'm going to put it again. Okay. And here, the decomposition. Another time. Okay. Well, once we have run the heat transfer analysis, we took this the temperatures and the degradation from this analysis and used as input for the residual the mechanical analysis. This simulation was performed in the same conditions as the test. That means we applied a tensile load of 20 kilonewtons during the first 5 minutes of the test. In this case, as in the heat transfer analysis, the material model for elastic properties that we use, is based on micromechanics theory. So the properties of the composite are derived from the subcomponents properties, and also they are dependent on degradation and temperature. As for the strength properties of the composite, we define them only dependent as temperature, and we calculate using this equation, optimizing the coefficients to fit the equation to the test data that we had. Here in these graphs, we can see the points of are the test results, and the dashed line are the results from the equations. And finally, we also consider or include in this mechanical analysis the Puck failure theory that was included in user-defined field subroutine to account for the strength of the composite material. We choose this method because mainly because it separates the matrix failure and the fiber failure, but also because it accounts for nonlinearities, and it's more accurate than others because it considers the matrix failure in brittle form. And here we can see some results from the mechanical analysis. On the left, we can see the matrix failure index and fiber failure index on the right. Here in the panel, in both of them, none of the elements failed, whereas in the stiffeners, we can see here some red elements, which means the failure index is over 1 in both cases. So in these elements, the simulation predicts a failure of the matrix and of the fiber. And just to conclude with my presentation, I would like to summarize some steps that we think will be very, very helpful to continue with this methodology. We think that it would be a good idea to invest more time in studying deeply the physics of the heat transfer analysis in composite panels. For example, taking into account the delamination that are produced during the decomposition we are not taking into account that, and we've seen that are very influence a lot in the results of the analysis or of the test. And also we would like to develop a more precise material model for the non-degrade range of the material. In the same way, we will, as for the flame simulation, the methodology that we develop maybe is not valid for all the situations, and we will need a more precise methodology, maybe performing some CFD models or another kind of simulation. And finally, to get this methodology fully validated, we will test or correlate it with additional fire test data and also with other structural details such as fastened joints or even composite metallic hybrid joints on other kind of details. And that's everything from my side. Thank you for attending this presentation. I hope you find it interesting.
Tiron, thanks a lot. It was really interesting. Thanks a lot. And I think I want to thank to all the speakers from the end-to-end analysis session. It was very nice with the introduction that you gave us on how we have done on analysis, but also on simulation in this project. I think that was an extremely important part in this project. Now, there are already some questions in the chat, and I would like to ask Rafik first. You have already answered lots of your questions in the chat. However, it would be certainly interesting if you can tell us in a few words on your SHM system about the accuracy and how you correlate them with other types of sensors. Can you give us a little bit more details on this?
So regarding our proof of concept, as it is mainly used to impact event, the idea is that we have to detect and localize the impact event within the FOD panel. Then the idea is also for sure to assess the damage that is within this related to this impact. And the idea is that we will use tomography to correlate, let's say, the damage characterization that we observe using an NDI inspection tools and the accurate data and the feature extraction from the different sensor data. Mainly from, if I talk about SHM, the interest is about fiber brack grading sensor and also PZT, maybe also strain gauge based on IFAM work. And if the question is mainly related to correlation, but for sure, so we will apply NDI inspection to characterize the damage and try to correlate this with the sensor, with the output of the sensor. However, as we are also interested about the stiffness degradation, the idea is also to measure the stiffness degradation and try to build, let's say, an empirical model that will correlate the loss of stiffness based on the damage index that will be developed in the algorithms related to SHM.
Great, thanks a lot. And I think that fits perfectly in this also in the talks from the other people, because it all interconnects very well. Thank you very much. Then we had
and if you just to allow me to add something,
yes,
so Frank has.
Go ahead.
So just regarding the Frank presentation, so one of the challenge of fiber optics is just to have, let's say, a high sampling rate acquisition. And here I see in your project that you have tried to deal with this issue, and this is a challenging topic, I would say, because actually we plan also to use fiber optics, but we are actually limited in the sampling frequency of the sensor node. But I take a note that you are also trying to deal with this. It's good stuff.
Maybe a remark from my side about this, Frank Godeman, is that currently there are systems available on the market for FBTs, which can sample already in range of, let's say, 500 kilohertz up to even the megahertz range.
Excellent.
Thank you.
Yeah, thank you. Certainly to you, Gideon and Frank, one of the things which was also asked, how to keep the fibers in place. And obviously that is an interesting question to you, or the answer came down from Wilco, or we also had some experience with this. And yes, as Wilco said, these fibers are normally fixed between the carbon fibers, so they don't move too much around. But it's something that you have clearly to address. But it's normally a rather limited problem. Do you want to add something to this?
Yeah, I can maybe, Frank Godeman again, maybe comment on this. That normally, yeah, if you embed the fiber, then what Wilco said is true. If you surface mount the optical fiber, then normally I think what you do is put the fiber with sealant fixed on the structure, and you have patch cables, like normal patch cables you use for other applications. Well, you have optical fiber patch cables as well. And they are well protected, and you normally use optical fiber patch cables to cover larger distances in airplanes, and only locally where you install the fiber brake ratings, you have a nearby connector to which you mount the patch cable. So in that sense, you only have to have a limited amount of sealant with which you seal the optical fiber to the aircraft structure. And sealing also prevents, let's say, the absorption of moisture by the optical fiber. And that depends on the coating, but that's something you want to prevent as well.
Yeah, great, thank you. And then we have in the Slido a question to Martin. How accurate is the surrogate? Can you tell us something on this?
Yes, thank you for this question. Yeah, for the surrogate depends, of course, on the number of training points that we have, and for the local buckling, the quality is really good. We use typical LIFO and out methods to evaluate the accuracy, and there we had like below 1% deviation if we apply this methodology. For the strength failure, it's much more sensitive because there are many different sensitivities that interact with that. For instance, the nonlinearity of the strength in different orthotropic directions of the CFRP. And therefore, we would suggest that we require more than the 100 training points that we had for achieving such a quality of the surrogate.
Yeah. There actually came in another question, which is if you can tell us something about the precision on the strength on at higher temperatures, also temperatures towards the glass transition.
Yeah, also a good question. Yeah, we have, as I have briefly introduced, we have used first by failure evaluation that are based on the unidirectional ply strength properties characterized within SuCoHS. I think Christian Brauner showed those results also, and they were also shown partially on my slides. And we used typical criterions and also compared Hashin, for instance, to Puck or also to Kunze. And one has to say that those criteria are probably not intended for this high temperatures where the resin softens and where the autotropy of the applied effective autotropy changes. We have already seen in our first test that we have performed that we would have, so we achieved test temperatures of 250 degrees Celsius, and by those experiments, the structure would have failed way below those temperature phases. So there's, of course, And a certain interaction between the 0-degree plies and the 90-degree plies, the transverse properties are always failing at first, of course, because the matrix in the interface is sensitive to temperature. This will be in the analysis the point where the structure fails. In reality, we see support by the rest of the laminate. So maybe, yeah, a more laminate-based error estimation is error failure estimation would be more suitable, and especially at those high temperatures, there's of course also different more work to be done on how failure mods vary and depend on temperature. Yeah.
Okay. Thanks a lot. Then we have a question to Juan. Do you think that if you consider the elimination with the structure, the difference between the experiment and the FEA will converge?
Well, that's a good question. We think so, mainly because having delaminations inside the composite is like having thermal barriers among between the layers, the different layers. So it decreases the rate of the conduction rate, and therefore the temperatures measured in the back surface during the test. That's the reason. Sorry, that's the reason, because the temperatures measured in the back surface during the test are lower and are not the maximum ones. So, however, in our simulation, the temperatures remain constant since they reach the maximum level. So we think we will get a better correlation if we account for the delaminations within the composite. Yeah, but we haven't performed any trial yet.
Thank you. And then also quite general question to you, which is, where is the limit of your model? Where do you see the limit of your model?
Actually, well, at this moment, the limit of our model is the correlation, and we haven't had we have just correlated with one test and one material and one kind of structure. So we will need to perform on more correlation, more use cases to try to find that limit. Yeah.
Then eventually one question from my side. What would be your idea? How many different materials would you need to test so that you have a better security for your model?
Oof, that's a difficult question to answer. But we will need to see. At least we will. I think we will need to correlate, or to try to correlate with the typical aeronautic materials, composite materials, which are the most common, the ones that we commonly use. And if we got good results, good correlation with that kind of materials, we can have a good model for our purposes.
Yeah.
I don't know if
no, it's clear. It's quite
yeah,
maybe
it's difficult.
Maybe I can also add something to that.
Okay.
We have also yesterday shown by Inigo, your colleague. He has shown the test pyramid, and we have in work package 3, which was this work package where we did the analysis. We have also compared within the development of the model at different scales. So the decomposition model, for instance, was validated at DC level. Then there were those honora tests at the plate facility and the fire facility. So we have really validated the model, or parts of the model itself, at different scales, and probably there is a requirement to investigate those limits of the overall model a bit further, but I would say that those different scales of validation feed into that. And just another question, Juan. Since you have modeled every layer, how long did your analysis require?
Well, it took too much time. Yeah, this one, yes. Well, this one took about 6 hours in a machine with 9 cores and I don't know 500 of gigas of RAM. So yeah, it needs a very powerful computer. Yeah. Yeah, and the mechanical one, since it takes some inputs from the heat transfer analysis, took more time, even more time than the heat transfer analysis, about 13 hours or so. Yeah.
Thank you. And these were all the questions which were in the chat.
Thank you.
I would like to open up the discussion to the audience. Do you have further questions to either Rafik, Gideon, Martin, or Juan?
Markus, I have just seen again that I can comment on those FPG questions. I think
Yes,
someone
please.
asked if there was a movement inside the panel noticed. And within the first test structures, we had a couple of delaminations within the structure due to moisture problems, which is fixed now. But at those delaminations, there is of course now so the fibers can move in those delaminations, and we have seen this on the output, of course. For a few other sensors where no delaminations were occurring, we saw a pretty good signal in between the strain gauges that were applied close to that. So I'm looking forward to next structure to have also a sight on that. So there were obvious delaminations, and now they are not obvious, at least. And I hope that such movement is not available there.
Yeah, I fully agree with you. It's really important to consider it and also to analyze if something has moved or not.
Mm-hmm.
Absolutely. Questions from the audience?
This is Tobias. I would like to ask also our consortium external members here, or how to say it, so Rafik, for instance, when you have now introduced us to the new Morpho project, which has just started, is there an activity inside your project to also have events to invite external, or do you consider an external group to be informed or invited to particular meetings in order to keep contact or maybe also to allow interaction between projects?
Sure. So within this dissemination, for sure, we plan also to invite partners outside of the project, let's say. But let me discuss with the chief of the project. But for sure, this is a good opportunity, let's say, just to cross, let's say, information and things like that. Angela? Maybe Angela is here also. Maybe she left anyway. But for sure, so Nikos and I will inform the project manager about it. Yeah. It will be a good opportunity because actually only the advisory board are invited, let's say, within our, let's say, meeting. But now we have another meeting, regular meeting in Greece during the last of April. But let me inform the project manager and get back to you.
May you recall who is partner of the advisory board? Can you inform us?
Yeah, so we have, as I said, can I share something just briefly? Just to show you the list of the advisory board. So this is the list of our, let's say, partners and also the advisory board. So we are 10 partners. So the project is led by Arts et Métiers. We have also universities like TU Delft, Patras University. We have also Synthesize, as you know, and things like that. So, and this is the list of our advisory board. So we have Simon Wade from the EASA. Hello, Simon. So, and
hi there.
So this is the list, Tobias.
Yeah, thanks a lot. Yeah, I remember you have shown that slide earlier, but thanks for answering that again. Okay. Yeah, would be nice to, we can talk about this later.
Yeah.
So, I'm not sure if there are further questions, as Marcus had asked.
I don't see anything anymore in the slide or in the chat, so I'm handing over to you, Tobias.
Okay, fine, we can do that. Thanks a lot. Yeah, so now I would almost say time is over, but not yet. Let me open the wrap-up session here. Just a second, please. Show my screen. Yeah, so I mean, there's not much need maybe to repeat everything what you said already, but I can say that at first I'd really like to thank everyone here for at first for preparing this project from the concept to a proposal which has been accepted. At second, to rework everything during this project, to settle everything, to be patient, to be proactive, and making the best out of what we have, coming up to extremely remarkable results of final demonstrators with individual new technologies. And I'm also happy that we not only end by technology development, but by having such an event like today. And I mean, in the beginning, we have been planning to have it physically, which of course would have been even much more interactive, much easier maybe to come into discussion, to also have interactive networking events and coming together, having a beer or a glass of wine is always easier than here via this screen. But nevertheless, I'm happy to have it, and I must say, maybe even there are some advantages that people had the opportunity to attend, which may not having the full time for traveling. So it also, I think we will keep some of those features also for the future for upcoming projects. Nevertheless, I would be happy if we could meet again physically in person, to meet in person, even people that have been attending this public workshop here who we don't know yet each other. It'd be nice to meet at the next occasion. So the first day was already very interesting. I was also very proud that colleagues from EASA and FAA have been attending and supporting us with their thoughts, and they offered also to keep in touch with us. So if you have further questions also in the audience, don't hesitate either to contact, for instance, Simon directly, or if you don't know each other, maybe we can bring you together in this case, or you ask us in this case. Today, we've been going into further detail, presenting all the different technologies, and also here, if there might be questions after the workshop that you forgot to ask, or that came up later in the discussion internally within your companies, your research organizations. Yeah, I think all of our members would be happy if you approach them directly. If you don't have their contact details on hand, just write a chat to Dominika or myself, and then we can directly bring you into contact, and we can take this time for that. Also, you've seen the virtual lab tours. It will be repeated now in half an hour, so you will have the chance to visit this virtual lab tour again if you didn't have the chance during the lunch break today. Thanks again also here, Wilco and Martin, for preparing this, which is quite an event for us. And now I would like to open up also some networking discussion. And to do this, Hauke Lengsfeld has joined as well this SuCoHS event today. He is from Composite United. And Hauke, maybe if you could introduce yourself briefly at first, and then you could directly speak also about the Composite United working groups on fire safety.
Yes, thank you, Tobias. So hello, everybody. So my name is Hauke Lengsfeld. I'm in real life, let's say it this way, I'm working for Structol in Hamburg. It's a relatively small company where we are developing and producing, for example, also flame retardant additives, mainly for epoxy, but also other reactive systems. And in this role, I'm also the working group leader for the working group fire protection in the Composites United. It's a very open group. I think we had already up to date three meetings in the last 6 months, so quite active. And of course, we are always happy to greet new members. We typically have 1 or 2 short keynote lectures about new developments, or it could be also some challenges, what you are working on. This is what we did in the past. Actually, we're about 25 members in this group. And in the last meeting, we had the idea came up to have a common goal, something like to develop and to work on a kind of specification or a norming specification to come from to get good results from small samples, and then to be able to make a prediction for large-scale fire testing. So to make life a little bit more easy for all of us. As you all know, large fire scale testing is always very expensive. So it would be good to have a lot of results on a small scale level to be able to predict at least a little bit more than today. So that's the idea where we are working now on, and I think the next session, we will have somewhere in June, July, and then let's see where we end up and how we can go on. So, as already said, we are open for new ideas and also new members. Let's discuss about this. Yeah.
Is there a question to Hauke? Maybe how to subscribe, or for whom it is intended? I mean, I think it's for all industrial and research organizations, right, Hauke? So to really bring together fundamental developments and final industrialization. And it's probably also not limited to Germany, or is it?
Of course not. Oh no.
Okay.
Everybody seems to be happy.
Yeah, nice to see. Yeah. So also here, we will be happy if we keep in contact also and to derive new ideas, continue from here on. I mean, this is certainly the last project to work on, and maybe the opposite, maybe a starting even for some of new ideas to see new opportunities for exploitation. And I was wondering if you have further feedback for us also as a consortium, if you can see some hints or also benefits from your side. So which might be the topics that you would like to have more information about? Is there something you'd like to mention? And can you give us some feedback about this workshop also? What maybe was okay, and where are some shortcomings which could be improved for the next time? Difficult question. Okay, so if there's anything you would like to mention afterwards, again, I'd be happy to receive that feedback. And so therefore, we are even a little bit faster than I have expected at the end to close this session. Let me thank you again, all of the attendances to give their input here, to ask questions. And therefore, I hope in this context to stay in touch, stay tuned with you, And so, Dominika, I'm not sure if you'd like to have a few words about subscription of the all the information that we've seen, because people will be informed about downloading. Do you have any additional information about this at the moment, Dominika?
Yes, so I think the first thing, Tobias, is that you did a very good job in promoting our publications and presentations website, because web page, because I've received several queries during the final workshop from several people who are trying to download the presentation. So it means that the message was well relayed, and I think many people got to know that such a web page exists, and all the public versions of the presentations from all the events in which the SuCoHS partners participated are available on our website. So don't hesitate to go there and download the files that are of interest for you. Simply, and you will see also a note that we have an open access repository, Zenodo. So we have a SuCoHS community opened on Zenodo, which contains all the open access publications that have been generated by the project partners as well. So this may be of interest for you. And other than that, we have a company page dedicated to SuCoHS on LinkedIn. So if you still want to keep in touch towards the end of the project, don't hesitate to follow and to subscribe to this company page. Unfortunately, SuCoHS is coming to an end, so now we will start communicating about the final results, about the closure of the project and the last public deliverables. But I think that there's still a lot of information, useful and valuable information for you to get, so don't hesitate to subscribe and to follow us towards the last months of the project and the closure of the project. And for the newsletters, there will be only a last one that will be issued, but it will be really just to communicate about the final publications and presentations and deliverables that will be available. So that would be all. And as Tobias said, we are here to answer your queries. If you have any questions, just don't hesitate to call us or send us an email. Thank you very much.
Thank you, Dominika, for your strong support here. Wouldn't have been such a success in this case as well, with all this background management for dissemination and internal project management. So then, yeah, thanks again. So all of you, I wish you a nice afternoon, and I hope to see you again very soon. Some sooner, some later, but hopefully to see all of you at some occasion. And then I wish you the best for the future. Talk to you. Bye-bye.
I'm back, Martin, so please start whenever you would like.
Perfect. So I will share my screen. Perfect. Can you still hear me?
Yes,
yes, very clearly. Yes.
Ah, this time it works directly. Perfect. So let's give it another start. So welcome back to the rematch of our lab tour. Here, welcoming you from the DLR Institute of Composite Structures and Adaptive Systems. My name is Martin Liebisch, and I'm responsible for the thermomechanical structural test facility, in short, Thermix. So within this SuCoHS project, we were investigating very demanding thermomechanical load conditions and fire scenarios for composite structures. Those load conditions are quite a challenge for material and structure. The plastic material of the composite softens with temperature, and so the composite properties degrade. The structural behavior overall deforms due to the temperature gradients impinged from the thermal loads. To tackle those challenges, we have developed several options. One option was the development of a novel material solution, a toughened cyanide ester developed by the partners NTPT and FHNW. This cyanide ester material can withstand higher temperatures and is applied still by typical autoclave curing of 180 degrees Celsius. Another option to tackle those high temperature requirements was investigated by further enhanced analysis methods that incorporate distributed heating to the structure and thus allows to increase the maximum surface temperature requirement. However, new material solutions and also new analysis methodologies require a specific validation. Such validation should be proposed by our structural testing, which is topic of our today's lab tour. You can see one of those test articles that is used for validation here. Another one was tested already within the project. How those are manufactured will now be presented by Wilco Gerrits from NLR. So Wilco, please give it a try.
Yes, thank you, Martin. So please let me share my presentation. So hopefully everybody can see it. Okay, so I'm not sure, maybe people overseas just logged in. Small introduction from myself. I'm Wilco Gerrits, working at the Netherlands Aerospace Center, better known as NLR. As a program manager, I started in '98, so it's quite some time in the last 15 years as program manager at the Composites department. So normal-wise, we would give an audience or people, during a physical meeting and a physical lab tour, so to show you along our facilities and show you the capabilities of NLR. Since we have a virtual lab tour and many movies are already available on the internet, I would like to let you know that on our website you can search for composites, for example. And on YouTube, there is a NLR Media channel where you can find a lot of movies also from our composites department. And if you go to our reports page and you search for composites, you will certainly find a lot of publications that we have written in the past. So please feel free, obviously, to visit these pages and find your information. This morning, I explained a little bit more about the 3 use cases that were already presented yesterday by the use case leaders. A little bit more in detail about the composite aircraft interior shell from Collins Aerospace. Just very briefly, the ANOVA case, and that will be more detailed during this presentation. And also a little bit more in detail about the nacelle use case from Spirit Aerosystems. Nevertheless, we also had sensor partners involved, and I will tell you a little bit more about that as well. So now we concentrate more on the ANOVA use case. Yeah, as already shown by many partners before, I think in many presentations you saw this information already. But what we did is try to find a stiffened panel that has blade stiffness completely integrated into to one part. So not having the T-shape co-bonded or co-cured system, but having an integrated blade stiffener system. Basically, it is a composite skin where we have embedded optical fibers by fiber placement. Will be shown to you later on in the movie. And what we did is by hot forming, creating U-shapes and then combining it together into to this stiffened concept. So here you see a little bit more details how the several parts are built up. The red part is the skin. In this example, relatively thick. The green part is an in-between laminate that takes care of the thickness of the stiffener, of the blade stiffener. And the blue part, as you see here, is a relatively thin skin, also fiber placed as a blank and then being hot formed. That will be shown to you in the next movies. So we had a pretty good experience with this, with let's say with other more common prepregs. The thing is that with cyanide ester, the viscosity is relatively low, so we had some issues during let's say M18. During M18, it was already quite in an early stage of the program. It was requested to already test the part. Of course, the Turnbeck's facility of DLR was had to be closed for some time, so we were not able to do some separate trials on cyanide ester. So it was a one go, and what we found out is that there were some imperfections, absolutely imperfections here in the let's say in the stiffener, as shown yesterday by FHNW, and these are things that can be solved, but for this let's say early stage one-shot panel, we found some imperfections there, and one of the reasons was that so besides, let's say, the relatively low viscosity of the resin, also that the filler that we have manufactured in UD material was a little bit too large, which gave us the problems that you saw in the section picture of Christian yesterday. Okay, the developers, or let's say designers, defined the locations of the optical sensors to be integrated into the skin of this panel. So that's something that we had to consider during the implementation of the optical fibers. And as already shortly shown in the movie this morning, is that we did a modification to the guides inside the fireplace machine. You can see it here in the middle, the aluminum brackets that we made with a conical shape inside, and let's say a hole diameter of 0.5 millimeters. That could cope for guiding the optical fiber through the machine. So obviously there are some what is it, feed rollers. So you see them here on the right side of the sheet. The feed roller takes care of feeding ore in the material. So the let's say the slit tape material, or in this example also the optical fiber. So we had to change it. You can imagine if you have this kind of a metal feed roller, that it will cut all the fibers into small pieces, so it will be a drama to use these rollers for the optical fiber. It will crush everything. So with the soft rollers, we had quite a good solution, and it was able to we were able to feed and also cut the fiber and then restart again. So it was quite a good working system. Took us some time to develop this, but finally it worked quite well. Here you see a movie about our experiences with fireplacing optical fibers. Here you see a little bit bigger, of course, that we have selected one of the 8 guides for the optical fiber. Here in this movie you see, and especially in the middle, that's also why we had the perpendicular directed fibers, to see that the location of the fiber itself. We did some trials, so with wide gaps and with smaller gaps, to see and to learn about the accuracy of positioning these fibers. Taking a piece of water, sorry. So here you see a very wide gap. A little bit further on, you see a narrow gap. And what you can clearly see is that the accuracy of positioning is not so bad at all. We also tried to do it with no gap to see if during embedding it was finding its way in between the fiber itself. But from experience, and this is the last one, very accurately in a narrow gap. From experience, we know that you need a narrow gap for fully embedding the fiber. The goal was to take a nominal thickness of a ply, which is close to the diameter of the optical fiber, and that's 0.15 millimeters. Going to the next slide. Yeah, so what we find out during all the trials that we did is that micro bending is giving some issues for optical fibers if you combine them and want to pick data during the curing cycle if you have involved optical fibers. As you might know, optical fibers are capable to measure temperatures and strains. So in terms of, let's say points of interest for temperature, could be helpful to have an optical fiber in a certain area. But also if you want to learn about resin shrinkage, maybe internal stresses by resin shrinkage after curing, optical fibers can help you to give you this information. What we found out is that if you want to incorporate them into a vacuum bag, is that undulation, or at least having a small radius inside the optical fiber, that you will lose signal. So the strength of the signal will be lost after having a couple of, let's say, small radius in the fiber itself. So we did some tests with several heights to see where the limitation is and to see when we lose signal. So for your information, losing strength of light does not immediately say that you cannot gain any data anymore, but at a certain point you lose that much light that you will lose signal. So what we did at NLR completely is development of let's say an extra bracket to release during application of vacuum and pressure inside an autoclave to release the tension on the fiber itself. So normal wise, if you put on the pressure, it will be positioned like this. If you see the green one as a tacky tape version, and this tool helps you to prevent that. What you see here is not only the optical fiber, but also having, let's say, a protective tube around the optical fiber. Everybody knows that optical fibers is very sensitive for damage and very brittle. So you need a tube to be, let's say, integrated into the composite material as well. What we have here is a very, let's say, simple solution, but effective solution. Because obviously after curing you want to trim your part, and you will still like to have access, of course, to your optical fiber. So this is one of the solutions that could work. Very simple but very effective. Yeah, then if you want to take signals from inside of the autoclave and having your interrogator on the outside of the autoclave, you need to go through the autoclave wall. So you have to develop a flange. This was done completely by photon first, so development of the flange, and then having the optical fiber going through the flange. On both sides of the, let's say the optical fibers, you will have a connector. So one is inside the autoclave over here, and not at the other side. So let's say the outside of the autoclave, you have to connect it to your interrogator. So then the connection is completed, and you can take data from the cure cycle as well. So not only photon first, but their optical fiber, but also the cure sensors from synthesites were involved during this use case for ANOVA. Here you see already the vacuum package of the panel itself. Here you see a separate panel where we have installed the durable sensor from Nikos, but in this package also the disposable sensors were involved to have an eye on the cure level during curing, and obviously, as Nikos already explained, so you can shorten your cure cycle if you know that curing is already on the requested level. So one of the developments during the project was the cure simulator. That's really a new finding. So then you don't need directly this special flange and all the connectors anymore. The thing that happens is that you have inside your material just one thermocouple, and this thermocouple is connected to the simulator. Here on top of the simulator, you have a small chamber where you place exactly the same material as applied in the package. And this heating system will take care of having exactly, it's a very reactive system, so it having exactly the same temperature as inside your package. So you can having your sensors here installed, having a very great system to see what the Q level is without having, let's say, special flanges and maybe temperature limitations. You only need one thermocouple and wire, and that's sufficient to get the system running. Very good system. And my colleague is still happy with the system of Nikos. So I learned from this afternoon that I have to switch to the video, otherwise we'll have no audio. So please let me switch to, maybe put on a camera as well. Switch to the movie. See what Ronald can tell us. So let's give it a try and listen to Ronald.
My name is Ronald Klom, colleague of SuCoHS, and just to show you today that we're doing a vacuum infusion with PMI resin using the isojet machine over there, tool and vacuum bag in the oven, and this equipment over here to monitor the resin resistance using the Shear simulator. And actually there's 2 resin arrival sensors in it as well, at the beginning, at the end of the laminate. We're just at the stage of warming up the resin for degassing, so we're monitoring the temperature and the resistance of the bit of resin in the Shear simulator with the temperature of the degassing as it is, which we now have to control using the flip controller from the temperature on the isojet machine. As soon as we're starting infusion, we're going to take the temperature from the oven and log it in on this one, and from there on we'll track and monitor the resistance of the resin while we're doing the infusion, get a better control of this tricky resin while infusing. Now we've started with the real infusion. The temperature in the oven 126 through the thermocouple, and if you then look at the Shear simulator signal, the temperature and the actual resistance, this is the line or the value that we're going to keep track of. If it rises above a certain level, then we're going to heat up the oven again to push the viscosity and get the last bit of resin in. Yeah.
So as you can see here, the system of Nikos is very helpful for us to understand and to develop, let's say, infusion systems, as well as you know, the optimization of Shear cycles. So please let me go back to the presentation again. So this is another video, can be run without audio. That was during our M18 meeting. For the people that haven't heard it before, that was just before COVID arrived to Europe and became critical. So you don't see any masks here and also no distance. So it's, let's say, the good old time. Here you see Rolf Evenblij from Photon First explaining his system. And here you see Alexander from Apodius explaining his system. And we had a live demo, of course, to show the capabilities of Apodius system. As already told before, unfortunately, Apodia is not existing anymore, but they have really a great equipment to do online monitoring and to directly put the information gained from the fire placement back to the database. You just saw very shortly that you know, during this demonstration also the optical fiber was fire placed, and here you see also the demonstration from Nikos during this meeting. Okay, back to the panel again, the Silent Ester panel for the ANOVA case. This is just a short part from the movie that's also online available from our pilot plant. So we are just starting it up. What you will see here is the pick and place unit that we have available over there, and the unit that you see here in the background, that's the one that we also have used for what is the hot forming of the U shapes. So here you see the laser tracking system, and this is a dry fiber system that's pre-compacted underneath, let's say the first vacuum bag. So with infrared is heated up, and vacuum will be applied to debulk the system, and having a stiff dry fiber preformed to be draped and cutted in the second stage of the process. So here you see the same process again, also with infrared heating, and to drape it on top of a certain geometry. So what we did for this use case is using the same system again. So here you see one of the trials where we did an investigation on the process window for this material, the cyanide ester material. There is some material here put in an envelope to be sure that there is no tackiness between tooling. So just let's start the movie and see what happens. So first, the vacuum system goes down, and we only apply a small amount of vacuum. Otherwise, we will have wrinkles inside. So we need to heat up the material to stay out of wrinkles during the hot forming process. The infrared unit moving on top of the material, and the material is equipped with some thermocouples. So what we will do with infrared is heating up in a short period, controlling or checking the temperature of the material, and when the material is on the right level, then we can apply full vacuum and drape the material around the shape. So obviously during the trials we need the thermocouples, to find the process window. Once we have figured this out, you can stay out of thermocouples because you know exactly what to do with this process. So here during cooling down, you see that there is a small second heating up for the distribution of temperature, also during cooling down. And then this is the final result. And also the inside will be shown now. So this is quite a good way to our point of view, to produce U shapes for this integrated blade stiffener concept. So yeah, in sequence here we have the fire-placed skin having the optical fibers with firebrake sensors already integrated, embedded, to be embedded and positioned with fire placement. Here we see the U shapes and also the in-between laminates, to assemble the blade stiffeners, the cold plates being installed into position, and then just closing everything, finishing the vacuum bag, and this package you already saw in one of the previous pictures during the autoclave process. So debagging is not in this presentation, but yeah, one of the challenges, of course, and the reasons for finding solutions is that we would like, to trim the part without affecting the optical fibers, so still having access to the optical fibers also later on. As presented already by Frank Groteman, this is also one of the possibilities to have optical fibers involved to localize impacts, and also to say something about the size of the impact. What could be extremely beneficial, of course, to learn about impacts on the products during lifetime, but also to focus on only a small area to be checked for damages during maintenance. So this is the final result with the sensors involved, and I think the latest, this one is the video again with the Apodia system. As already told before, yeah, it's really a pity that Aporia is not existing anymore. They have really, to our point of view, really a great system that could be very helpful for us to develop for further development. For the track record of each ply, you have detailed information inside your database available. And even, you know, if you find, let's say, defects out of specification, you know where they are, and you know after each ply you can still correct the problem and save the part. So it's really a very nice system. And we were not able to buy it because, you know, what is support is needed if you want to work with such a system. And that was the only reason not to buy it, and that's really a pity. So that was yeah, the virtual lab tour. Again, if you want to see more from our equipment, you can find it on the website and on YouTube. And if you have questions, feel free to contact me. That was it.
Yeah, thanks, Wilco. So I guess I should take over again.
Yes.
So you should already see the screen. Can you still hear me? Perfect.
Yes, we can.
Yes, yes.
Perfect. So we are starting with the second part. Wilco just told us how the structures, the test articles are manufactured, and I'm standing here at our facility within the sample preparation area where we apply sensors to the structures. I will initially explain about the sensor equipment. Later on, we will go into the facility where I explain more into detail how the structure is clamped within the structure, how boundary conditions are reinforced, and how the test is conducted. And at the end, we will conduct together a live test. So the objective, just to repeat, the objective of our testing is to investigate the structural behavior that results to varying thermomechanical conditions, varying temperature fields, and simultaneous mechanical loading. We want to demonstrate the structural performance at those deformations and also at elevated temperatures. And we want to get validation data, a specific database that is validating our numerical analysis. So for this, we need quite a lot of sensors, spatially distributed in order to measure our structural deformation all over the structure. As you can imagine already by those cable trees that we can see here exiting, it's quite a lot of sensors that have to be applied. They have to be capable of the high temperatures that are applied within testing. And I've placed here another camera that looks onto the detail of the structure. So, for instance, on this skin field here, you can see 5 different strain gauges that we applied. Those strain gauges are measuring the strain. We have different types, so rosettes right over here, or linear ones. And they are capable to measure strains up to 350 degrees Celsius. Right next to each of those strain gauges, we have placed a thermocouple measuring the temperature. The temperature close to a strain gauge is important to correct the strain signal that we receive. Temperature influences the strain signal by a temperature-dependent K factor, so the measurement coefficient, by thermal strain output, and also by a thermal mismatch between the strain gauge CTE and the composite material CTE. So we require those temperatures to correct the signal and achieve the correct strains. We've placed thermocouples all over the panel, like also here in the stringer foot or on the top of the plate, also over there. And we've placed those sensors, so both strain gauges and thermocouples, with using polyamide adhesive, also seen by those yellow dots here. This polyamide adhesive can withstand temperatures at similar way, so up to above 300 degrees Celsius, but it needs a special curing process. So initial curing, also applying a certain pressure to the object that is adhered, is performed at 200 degrees Celsius mainly, and afterwards we need a freestanding post-cure at temperatures close to the service temperature. As you can imagine, applying all those sensors, also here at the stringers and at both sides of the structure, applying all those sensors within an extra curing step is quite a significant challenge and very time consuming. And therefore the option of integrated fibers is a good option, at least for our testing and probably also for reality. We've heard a lot of those optical fibers. And one optical fiber is placed exactly here below those strain gauges. So the first FPG sensor is right here, the second one, third, etc. And the fiber exits the structure right over here. The exit is conducted by omitting the top layer so we can move out the bare fiber. Then the fiber is coated into this temperature resistant peak tubing right here at the end. Then it goes until this improvised setup. We improvise the setup in order to keep the high temperature resistant tubing out of the oven, which the oven we need for applying those sensors. You can also imagine here somehow how small those optical fibers are. Then they are coated again and go to this not anymore temperature resistant tubes, which are then plugged into the interrogator and the computer system. We have placed always a back-to-back strain gauge onto the structure where also a fiber break sensor is located. So for instance, in those positions, so we can later on, we have a lot of information in thickness direction. So 2 strain gauges at the surfaces, one fiber break rating in the center. And by this, we have 3 strain measurement points in thickness direction at those positions. And we can also compare if the strains measured with the optical fiber are correct. So that's anything to say about the electrical sensor application. Before we mount the test article within the facility, we have to conduct an extra step, which is applying a certain coating to the structure. I'm showing here the first test article within the SuCoHS structure again. We apply a black coating on the heated side. It ensures that there is a uniform emissivity, ensuring uniform heating by the radiation. On the top side, which is visible for the digital image correlation system, we have a black and white sparkle pattern that is a requirement for the optical system to measure deformations, strains, etc. You can see here at the ends where no coating is applied. This is where the structure is integrated to the facility, and we will have a look now into the facility. So this is our thermomechanical test facility, or in short again, Thermex. You can see the test article right here in the center. We've currently applied a test article that has only 2 stringers. It's a bit smaller, but similarly setup overall. So the test article is right over there. You can see that it's that we are having the fixed clamp at this side, so not movable. This one is movable, and the test article is then placed somewhat like that. So again, with the black-white sparkle pattern to the top, so we can measure the global shape of our deformations with the optical Aramis system, or by digital or also the thermography imaging the global temperatures. The structures can have a maximum dimension, a maximum length of up to 1 meters or 0.8 meter width. We can test structures of a maximum thickness of up to 10 centimeters. So any kind of different structure within that limits can be tested. Honeycombs, curved structures, different ones, also assemblies is possible. So let's go into further detail how the facility is working. I've put a scheme of the facility right at the front here. At your left side over there, we have the fixed clamp. At your right side, right here, we have the movable clamp. Behind the movable clamp, we have this blue frame here. From this blue frame, there is the motor located, which applies forces of about 400 of maximum of 400 kilonewtons onto the structure. You should see some arrows that are showing how the force is applied within the current setup. So we are currently applying axial compression forces onto the structure. In simultaneous, we can also apply heating to the structure, so one-sided heating. Heating is provided by the infrared heaters that are located below the structure. You can also see them through this little window here. The infrared heaters have a total power of 2 times 85 kilonewtons. With this electrical power, we can reach temperatures at the structural surface of about 1000 degrees Celsius. Temperatures are controlled usually by a thermocouple. So the electrical current, the electrical power of the units is controlled, of course, by the sensor. And we are currently using in the setup a thermocouple that controls the electrical power, but we can also use other sensors like heat flux density sensors, etc. So in between the infrared heating unit and the structure, we can place apertures like I'm showing here at the front of the facility. So placing the aperture between infrared heating unit below and structure above enables a local heat impingement through the hole. So only the radiation comes only through this little hole and produces a distributed heating onto the structure, which is at top here. We can adapt our apertures according to our wishes. As you can see right there, a different option. They are finally located in a frame, in a metal frame like this, which is then mounted between infrared heating unit and the clamps. So let's take a look below the facility. We are having here the option where we can mantle the aperture frame. On the left side and the right side, you can see the clamping. On the lateral sides of the structure, you can see that there are isolation blends, isolation blankets. Those are required to ensure that we have time-wise uniform thermal boundary conditions. So at this side, we have the hot thermal boundary conditions. At the top of the structure, we have ambient boundary conditions. Yeah, and of course, the structure in black. So let's have a short view on how the setup is looking if we are heating the structure. So the heaters produce quite some warming. They are now on the full power setup. When they later on, you will see that within our live testing, when they are reaching the target temperature, they will begin to oscillate in order to keep the target value. Further on, I've placed another camera right on top here, and we will switch to this camera to have a deeper view onto the structure. So you can see here the two-stringer structure. On the lateral edges, again, the isolation blankets, which ensure that there's no hot air coming around the edges from the hot side, and which ensure that we have our ambient conditions over here. The structure is clamped here at the movable side, at the load introduction, and here at the clamped side within those potting frames. The potting frames use a specific concrete material that can resist high temperatures and that have a low thermal expansion coefficient that is close to the composite material. They ensure that loads are introduced without kinking of the structure close to the cross-section area. Another interesting fact of those potting frames is that they are segmented. You can guess it from those lines here which show the different segments. The segmentation and cylinder roller bearings at the rear side of the potting frames allow transversal movement. With those transversal movement, transversal thermal expansion is allowed for the structure. And finally, stress concentrations due to such reinforcements are reduced if you wish that. So that's how the structure is clamped within the facility. You can see here the local sensors that are applied to the structure. We are further using displacement sensors that are measuring the out-of-plane deformation here. We've placed some at the structure and some at the potting frames, or even behind at the clamps, just to ensure that the load introduction is not making any kind of rotations. At the lateral sides, right over there and over here, you see laser triangulation systems and further displacement sensors. By those systems, we are measuring the axial deformation of the panel, and together with the measurement of the applied force, we will then get our load shortening curve and can derive the structural stiffness. We've also placed two of each sensor, so one over there at this side and one at this side, to track if there are any kind of rotations within the specimen plane. So that's everything so far to mention about the mechanical test setup. I will now go back into the control room and let's test this structure. Okay, you can start the measurement. So you can see right here the measurement is starting. We have placed on the left side, we have placed the local sensor signals. At the top, you see all thermocouples placed within the chart. Quite close to the chart, we are showing the thermocouples that are by their numeric quantity, the thermocouples that are placed within the central skin field. Below that, we are similar for the strains. So all strain gauges applied are shown within the chart, and only the ones located within the central skin field are shown by numeric quantities. At the lower left, we are showing the load shortening curve, so force over axial shortening, and you can also see the force by its value and axial displacement. Yeah, on the top, you see those two camera images that we had recently shown within the facility. So you will notice there how the infrared heaters will oscillate after reaching the target temperature. At the center right, you see the thermography image, and at the bottom right, you see the Aramis, so the out-of-plane deformation measured by the Aramis system. The Aramis system probably has some lag, so I've put it in there, the force and the temperature. So let's have a deeper look on the setup of our testing. So how do we apply temperatures and mechanical forces? We start initially at room temperature conditions, as we have recently seen, then apply the heat one-sided until position 1 here. This is where we reach our target temperature in thermocouple 1. The target temperature of this test we were conducting is 150 degrees Celsius. After that, we are heating through the structure up to position 2. The blue line in position 2 shows the force. So we have a certain pre-force active at the moment. From this state onwards, we have a stationary state and we can remove our force up to position 3. Within position 3, we have 0.5 kilonewtons, so that's our starting force of load, and apply then additional forces up to our target load of 35 kilonewtons. After that, we remove the forces again and yeah, cool down the structure and test is fixed. So let's start with testing. Okay. So, as you can see, yeah, nicely within the thermography image, sensors and stringer food certainly act somehow as heat sink. Structure is heating, and as it heats through, this thermal gradients will reduce somehow, but will be existing for the whole time somehow in a stationary state. On the top left side within the temperature measurement, you can see that we have reached now our target temperature. This you can also see on the cameras on top right that the infrared heaters are oscillating now. We can see that thermocouple 8 is overshooting a bit. This is due to the nonlinear power output of each infrared heating unit in axial direction. So at its end, the power is a bit less high. And the specimen is not aligned concentric over the structure. So the strain gauges have almost reached a horizontal way, so we can reduce our force now to our starting point of 0.5 kilonewtons. You will see also in the lower right in the RMS picture that our deformation changes now. We've reached our starting force. You see some adaptations also within the strain gauges already. They will start deviating when we apply our mechanical force. Okay, we can apply it now. So now we are increasing our load again up to 35 kilonewtons. You will see the load shortening curve on the lower left, increasing partially. Above that, the strain gauges are acting accordingly. The out-of-plane deformations on the lower right, you can see they are lagging a bit behind the force. But you can see that the outer skin fields show, yeah, the biggest deformation. Unfortunately, the local buckling that we were intending for was not reached. This is probably due to the, yeah, 2-stringer setup only and the free edges. However, the free edges change now their, I would say, buckling pattern, their pattern from a single deformation due to a 3 or 4 wave pattern, what we can say. We've reached 30 kilonewtons and we'll approach our target load of 35 kilonewtons soon. You can see that the strain gauges, 2 strain gauges are behaving in tensile direction, the other ones are in compressive direction. So we can remove again our forces after a little period of holding the force. That's basically everything to say. We are just reducing it to a final end step, but the main things that we wanted to show are already shown. So I will continue. So the tests that we have just seen are performed for different thermal loading conditions, so placing different apertures between heaters and structure. This test was just without aperture, global heating only. We repeat all of those thermal boundary conditions for different target temperatures. So beginning at room temperature and then iteratively increasing our target temperature within the structure until our final temperature or is reached or the structure collapses. In between every temperature test, as we just performed, we are conducting reference tests at room temperature. By comparing reference tests at room temperature prior and after each thermal test, we can see if there are any damages, if there are deviations compared to the usual behavior, and track thus if there are, if anything has changed. By this, we produce tons of data. We are measuring if our material can withstand the temperatures we were intending for. By this, we can demonstrate the performance of the structure. We can investigate the mechanical behavior at different thermal load conditions. And of course, the data serves also for comparing to our numerical analysis. So if you're interested into the topic or into further capabilities of our facility, further boundary conditions that we can apply, further options, you can just contact me by myself. You will see on the right my contact data, or you can also have a look on our institute page, which you can reach over the QR code on the right. Thanks again to all partners for the great project, for the great collaboration. It was a pleasure from my side. Thanks again, and if there are further questions or anything to mention, that's it from my side.
Thank you very much, Wilco and Martin, for having shown us once again these very interesting lab tours. So I'm just checking if Tobias connected again because he had to leave a little bit earlier, but I think he's not in the participants list yet. So just, once again, thank you very much. I will just check. Sorry, So
thank you to you too, Dominika, for hosting all the projects. It has to be said.
Yeah, but as I already said, it was a big pleasure for me. So I'm happy that you found my support useful. So I'm happy that the collaboration was so fruitful. And I'm just checking the chat and the Slido application in case there are any other comments from the audience, but I cannot see any new messages appearing. So
I just had an idea. At the end of my presentation before.
Go ahead.
Because we have just produced the second SuCoHS structure and we will begin testing in, I would say, a month or so. If someone is interested, you can also give it a news on the homepage. If someone is interested, you can just write a message to Tobias, to me, or maybe to you also. If there are some interested people, we can plan again a live test somehow. Maybe not with such a strong time limit as we have now. And if there are further questions, we can discuss them in another SuCoHS live event. So this was just an idea.
Very
well.
well.
There are interested people.
So we will communicate about that. That's a very good idea, Martin.
The dissemination is still ongoing.
Yes, and now it's the most intense part, so...
Yeah.
Okay, so I think now's the time to really say again a big thank you to all the presenters, to all the moderators of the workshop, and once again to Wilco and Martin for having walked us through the lab tours. Also a big thank you to all the participants. Some of them have already left, but I hope that you enjoyed the workshop and that you found it interesting and useful for your professional activities. Normally, you will get the contact details of the presenters in the contact information slide at the end of their presentation. So as we already said, the dissemination material from the workshop will be available very soon. So look out for this on the project website. And meanwhile, if you have any other query, don't hesitate to contact Tobias or me directly, and we will be happy to discuss. And so I think with this we can close the workshop, and I would like to wish you a very nice afternoon, and I hope to hear from you very soon. Thank you very much.